The cryosphere is the ice mass of our planet, the ice sheets, permafrost and water ice of the poles. A moderator of ocean and atmospheric temperatures, a sun reflector, the cryosphere is an integral part of this planet's cooling system. Climate change is shrinking the ice caps, and it's a runaway effect. Our world is warming, the oceans are rising, and we need to do something about it. Of all the fresh water on Earth, 99% is stored in ice sheets, the large frozen masses that form over land. As climate changes, melting ice sheets can contribute to rising sea levels, which can place vulnerable cities around the world in jeopardy. From the South Pole to Greenland, from Alaska's glaciers to Svalbard, NASA's Operation Icebridge covered the icy regions of our planet in 2017, with a record 7 separate field campaigns. The mission of Icebridge, NASA's longest-running airborne science program monitoring polar ice, is to collect data on changing ice sheets, glaciers and sea ice, and maintain continuity of measurements between IceSat satellite mission. World-renowned leading climate scientist and astronaut Dr. Piers Sellers was director of the Earth Science Division at NASA Goddard. Having seen Earth from space on 3 shuttle flights and 6 EVAs, Dr. Sellers was deeply concerned for the future of our climate.
Now, Icebridge is probably one of the most important field campaigns we have running right now. The world is warming, and it's warming faster in the north, around the Arctic, than anywhere else by a factor of 2.5. It's 2.5 times increase in warming here compared to the global average. So this is where it's all happening. And as a consequence, the ice is melting fast. It's melting on the Arctic Ocean, and the ice mass on top of Greenland is melting and falling into the Atlantic. So we're mapping that using aircraft and satellites where we can. And of course, we've got people on the ground checking against these data as well. So this is ground zero for global warming. We're doing a lot of work here. We put a lot of effort into it. And I think it's paying off in terms of improved understanding.
Operation Icebridge began in 2009 and continues to fly aircraft through the region with advanced sensing equipment and coordinated land traverses by scientists to ensure accuracy of satellite data. Now, in conjunction with the European Space Agency, they coordinate and share data with additional satellite assets which fly identical science instruments. Just why are the ice caps melting? Because of the so-called greenhouse gases: carbon dioxide, methane, nitrous oxide, and fluorinated gases in the atmosphere. Together, they heat up the atmosphere by trapping energy. While CO2 has always been part of the atmospheric makeup, it has changed since the Industrial Revolution.
In the pre-industrial age, the CO2 response to temperature was that the temperature would go up and CO2 would go up. or if the temperature went down, CO2 would go down. And the reason for that is when the temperature went up, the whole biosphere revved up and emitted CO2, and we had more CO2 in the atmosphere. So we understand that process. The problem for the science community is in the post-industrial age, the CO2 rise is preceding the temperature rise. So two different things happened. One, pre-industrial, where temperature was driving the CO2, post-industrial, where the CO2 is driving temperature, which means a completely different physical, biological process is going on. And we don't understand what the consequence of that change is. It is a fundamental change to how the Earth works and how the Earth's radiation balance works. And so, since we don't understand it, we're very concerned because we don't see any restraining force on continued increase in temperature due to continued increase in CO2. And that's a problem.
Warmth tipped the scales again with the hottest October on record, but also the fourth hottest year to date for the globe, according to a fresh analysis by scientists at NOAA's National Center for Environmental Information. Generating long-term data sets is extremely important when studying climate. So, to maintain continuity, a new generation of Earth observation satellites are coming online. ESA have deployed Aeolus, METOP-3, Sentinel-C, and NASA have launched ICESat-2, the JSSC, and the follow-on GRACE missions. All of these satellites have one instrument in common that measures altitude.
A radar altimeter is a beautiful instrument because it measures almost everything we need on the planet. It measures the height of the sea, the height of the ice caps, but also we can use it to measure the heights of lakes and rivers, even derive river discharge.
METOP-C, the third in the METOP program, carries no fewer than 13 observational instruments. Some are identical to NOAA's suite of satellites.
We have 10 instruments on board METOP. It was a very large platform. And these instruments are also provided by different organizations. We have a set of instruments provided by NOAA NASA. We have instruments provided by CNES. We have instruments which are procured by ESA, and some other instruments which are procured by EUMETSAT directly.
So METOP-C is the last satellite of a cooperation program that we have with the NOAA in the United States as part of what we call the initial joint polar system. So in 1998, EUMETSAT and NOAA signed this cooperation agreement where three European satellites, or three METOP satellites, were corresponding to three US satellites. And for these satellites, we share instruments so that the users get information from both satellites, the same types of information. So we try to create synergies between US and Europe, more benefits to our user.
We didn't expect we'd be able to measure sea level to just a few millimeters every 10 days. And having such accurate measurements for 25 years let us monitor sea level rise and even perhaps detect an acceleration in the sea level record. And that was something that wasn't envisioned 25 years ago. But as the technology has gotten more and more accurate, we've been able to make more and more accurate measurements of sea level. And so we can be even more confident in our results. Combined with, we have other observing systems other than altimetry. We have a gravity mission called GRACE, where every month we weigh the ocean. And we have robots that float throughout the sea, about 3,000 to 4,000, that take the temperature of the ocean every few days. So when we add up the results we get from the gravity mission where we weigh and where the Argo floats where we take the temperature, we get almost exactly the same answer that we get from the radar altimeters, to within a few millimeters. So we're very confident in our results that we're seeing 25 years of sea level rise of about 3 millimeters per year, which doesn't sound like a lot, but as we see it starting to increase year after year, we know that acceleration will be very devastating for coastal communities all over the world.
Aeolus, ESA's newest Earth Explorer satellite with which the agency will measure wind profiles from space with laser technology.
At the moment, we have a very poor understanding of how the wind is around the globe, and we need more knowledge about that. But that's the information you need to start. You need to have a picture of how is the weather now to be able to predict how the weather is in the future.
Aeolus is a relatively short mission to demonstrate the potential of the Doppler wind LiDAR in space. And once we can demonstrate that actually it's made a decent impact on the numerical weather prediction forecast, then hopefully we can have an operational follow-on mission, or maybe several satellites in tandem rather than just one satellite. It's not just wind information, actually. You need to also know temperature information, pressure, and humidity information. But the winds are a key component of that information that you need to know right now to work out the weather in the future.
Sentinel-3A was launched in 2016 and 3B in 2018. Both satellites primarily focus on our oceans. They measure the temperature, color, and height of the sea surface, as well as sea ice thickness. These measurements are needed to study changes in sea level, marine pollution, and biological productivity. Sentinel-3A has already yielded interesting results.
The Sentinel-3 mission is actually quite a versatile mission in the sense that it serves a large variety of different Copernicus services. So we're not just working with the Marine Environment Service, we're also working with the land, with the atmosphere, and with the climate service. There's a large variety of data that we can actually supply. The Marine Service is probably the most developed for the moment. It's already using data over the ocean, in particular the ocean color data, which tells us something about the marine ecosystem, about the health of the sea, and can basically also predict something like harmful algal blooms. Snow cover gives us an idea about the snow water extent. So basically that gives us an idea of when this melts, for example, where we go in terms of flood forecasting, runoff models, so for hydrological applications, but also for weather forecasting, for example.
Sentinel-3 mission is supposed to last until 2040 at least. So A and now B will be in space soon. The C and D model, which are replica of this one, are under manufacturing now and will be completed by the end of the decade. And they are expected to be launched in the 2023-24 timeframe to cover basically the Sentinel-3 mission until 2030.
That's why we want to have continuous measurements. So we have planned with the next series of JASON missions, JASON CS or Sentinel-6, that we'll have at least 10 more years of measurements because we need to keep monitoring the sea level as it accelerates.
With this long-range forecasting, the acceleration of global warming can be monitored and better predictive models developed.
Yes, that's why by having all three measurements, that helps us understand the cause, that we can see from GRACE a measure of which continents the water is coming from, that Greenland and Antarctica are melting, and some glaciers are also melting. And we can also see as the temperature of the globe increases, we can watch the water in the ocean actually expand for more and more heat.
Scientists on the ground continue to innovate ways to improve satellite data accuracy. Surfing for science may seem far-fetched, yet that is exactly how Dr. Bob Bruin of the Plymouth Marine Laboratory is pioneering a new technique in satellite oceanography. By equipping his surfboard with a device called a smart fin, Bob can measure sea surface temperature and motion of coastal waters with his smartphone. Later, Bob can use the smart fin data he has gathered to better interpret Sentinel-3 satellite data. The Sentinels are part of the Copernicus program. Using the three instruments on board, the satellites gather information on ocean color, water quality, changes in sea level, and, most important for Bob's research, sea surface temperature.
With over 40 years of thermal radiometry we have now from our satellite platforms, we can begin to get a really good understanding of how temperature is changing in the nearshore environment. And temperature is a critical component of our oceans. It controls the biology, through changes in growth rates and reproduction. It controls the physical environment. Together with salinity, it controls the density of the ocean, how coastal currents move, and it's also a fundamental component of marine chemistry. The reaction rates of many chemicals are temperature dependent. The gases that move from the atmosphere to the ocean are temperature dependent.
In situ data gathered by scientists like Bob is extremely important as it complements and helps to verify data provided by the Sentinel satellites. For example, the temperature of coastal waters is difficult to measure from space, though they have very high levels of marine biodiversity. So scientists find new and ingenious ways of increasing the number of in situ measurements in these waters. With the SmartFin, for instance, surfers and other water sport enthusiasts can gather data while enjoying their hobby. Meanwhile, NASA has dispatched 2 new satellite missions to observe the most critically changing regions, the poles. NASA and the German Research Center for Geosciences, GFZ, has launched GRACE-FO, continuing the revolutionary gravitary measurements of its predecessor, GRACE. ICESat-2, with an advanced laser altimeter system, is continuing the work of its predecessor. This new technology will help study ice sheets, but also sea ice, glaciers, permafrost and snow cover. Collectively known as the Cryosphere, these frozen zones help sustain stable conditions for life on Earth.
ICESat-2 is NASA's latest technology to measure the elevation or the height of ice sheets, and by repeating those measurements through time, we can measure how ice sheets are changing. It'll also allow us to measure the height of sea ice, which is a way to understand the thickness of that sea ice. And so it's really a huge advance forward in both our precision of elevation change measurements as well as coverage. Each of those 6 beams gives us much more data than we've ever had before. ICESat-2 was designed and built here at NASA's Goddard Space Flight Center, and it does take advantage of many of the latest advances in that technology. It's really an excellent tool for studying changes in ice sheets and in sea ice. For sea ice, it's really critical. It plays a first-order effect in weather patterns around the world. Sea ice in the Arctic Ocean regulates the exchange of heat and water vapor between the ocean and the atmosphere. And as sea ice gets thinner or thicker, it either allows more or less of that heat exchange to happen. For ice sheets, as that ice is lost back to the ocean, it directly goes into sea level rise, which of course impacts folks worldwide.
So NASA scientists crossed the Antarctic, taking altitude and radar depth measurements to help calibrate ICESat-2's instruments.
One of the other experiments we were doing is leaving out what we call corner cube reflectors to get an assessment of the pointing of ICESat-2. When we make an elevation measurement, how are we sure it's in the right place? So in this picture, you can see a bamboo pole with a little white cap on the end of it. And embedded in that cap, a little piece of glass about as big as your pinky nail, and calibrated to return green laser light from the satellite.
With the requisite observation tools in place, the next step is to interpret the data.
Ice sheets are actually really dynamic, and they flow under their own weight from the center of the ice sheet out to the perimeter of the continent. In the really cold regions and way high up on our ice sheets, we get a lot of snow accumulation, and over time, that accumulation can build up. If it stays cold enough and that snow persists, and then you get another year of snow and another year of snow, you can imagine the weight of the snow on top of itself forces some of the lower layers to compact. We call that the firn densification, the top layer of the ice sheet. When we talk about the health of our ice sheets, we talk about the mass balance of the ice sheet. Basically, that means coming in is in balance with all the terms of water or ice going out.
The health of the ice sheets depends on a balance of these terms of input and output. But the interaction of the atmosphere, ocean currents, and temperatures can force the ice sheets out of this equilibrium.
At a big scale, the winds in Antarctica are kind of spinning in a big clockwise direction around the continent. But you can imagine a big dome of ice has very little obstruction, like trees or mountains kind of steering the winds. Consequently, winds that sort of are gravity-driven and come down the continent can build up speed really quickly and, again, uninterrupted by any sort of disturbance. And we call those katabatic winds. And they have a major influence on what happens at the edge of the continent. Around Antarctica, there's a massive current that we call the Antarctic Circumpolar Current, and it flows clockwise around the continent. Close to the continent, we also have the Antarctic Coastal Current, stays really close to the coastline and flows counterclockwise around the continent. In addition to these continent-scale currents, we also have regional-scale currents, such as gyres. Gyres are these parts of the oceans that are sort of isolated because of topography or ocean bottom topography. They're usually closed currents that often circulate. The gyres have a big role in sea ice formation and also in the currents that actually flow underneath our ice shelves. You can imagine that around the edge of the continent, near those ice shelves, warm water from the ocean can intrude into that cavity and contribute to basal melting, the melting from warm ocean waters of the bottoms of our ice shelves. Calving in Antarctica is a little bit sporadic and it's hard to actually model, but some of the contributing factors associated with calving include those strong katabatic winds pushing on the edge of the ice sheet, pushing on the edge of the ice shelf, and calving large icebergs. So we're measuring surface elevation, and we can take that vertical measurement, kind of integrate it over the whole ice sheet and get a volume change. And then the real science of ICET2 is taking that volume change and turning it into a mass change. And from that, we can determine how much ice is actually turning into water in our oceans and raising sea levels. So the Greenland ice sheet is thinning, and it's thinning variably, but mostly along the coastlines. It's thinning beyond our expectations. And all of that thinning is taking place upstream of where the ice sheet is grounded. Therefore, that is going right into the ocean and contributing to mean sea level rise.
Since we launched ERS-1 in 1992, we have been working on the radar altimeter time series, and we have derived a 25-year-long time series of sea level rise. Sea level rise is a major indicator of climate change because it integrates, for instance, the melt of Greenland and Antarctica. We have analyzed this series and we have analyzed the error, which is under control, and so the scientists are convinced that now we have clearly on average 8 centimeters of sea level rise, but we also have regional variation. For instance, in the tropics, it's 3 times that value. And what we have also analyzed with the recent data is that in the last 5 years, sea level has been accelerating. So it's not 3 millimeters per year or 3.2 millimeters per year. It's more like 5 millimeters per year. We have provided this data to people doing projections, to scientists, climate change scientists doing projections, and they have modeled the sea level in 2100, which is expected to be 2 meters higher than today.
This animation shows how different the globe will look by then, and prompts us to consider where the food and fresh water will come from. Set the controls for the heart of the sun. It's a dramatic statement familiar from movies and music, but now a new mission really is ready to plunge into the atmosphere of a star. Not just any star, our star, the Sun. 60 years in the making, the Parker Solar Probe is primed to reveal the true nature of the heart of our solar system and the source of the solar winds.
9, 8.
Weighing just 685 kilograms, the solar probe was launched aboard a ULA Delta IV heavy rocket. Its thrust of 9,700 kilonewtons may seem like overkill, but the Parker probe has to travel faster than anything before. As a matter of fact, it will be the fastest man-made object ever launched.
Parker's solar probe really is a historic mission. It was first dreamed of in 1958, and it's remained the highest priority mission throughout that period. The reason it hasn't flown is just because it's taken a while for technology to catch up with the dreams that we had for this amazing mission.
Destined for the Sun, our star, this probe is the realization of a dream that has been evolving over decades through the talents of hundreds of dedicated people.
After working on this for 10 years, it is really a pleasure to see it kind of actually coming to fruition. To be one small part of this huge engineering team that is making science dreams come true is just amazing. I can't wait to rewrite textbooks and change the way we look at the sun forever. I'm really excited to pass this off to the mission operations team and see all the science data that comes down and just get to enjoy all that Solar Probe brings us.
This is a 60-year journey that people have gone on to make Parker Solar Probe a reality. And to be there at the finish line, that is definitely the coolest thing about my job.
Several questions arise. How did this project get started? Who was behind it? And why is it called the Parker Solar Probe? It's because of this man.
The Parker Solar Probe is the first mission ever to be named after a living person, our own University of Chicago astrophysicist Eugene Parker.
Born 1927 in Houghton, Michigan, Gene Parker gained his PhD from Caltech in 1951. By 1958, he had developed his theory on the supersonic solar winds and predicted the shape of the solar magnetic field in the outer solar system, which now bears his name, the Parker Spiral.
So Gene Parker had graduated in physics and had a hard time actually getting a job. So he was first doing some researching at University of Utah when he was then invited to come to Chicago. He was not sure he was going to make it in the field. When he wrote his paper, it didn't help that the referees were not in agreement with him and didn't really want to publish his work. So he had lots of challenges early on, but he was right. And this is one of the things that first helped him, be the person that we all recognize as this amazing role model to all physicists, but also the power of science being right or wrong due to experiments. So what vindicated him was not just having Chandrasekhar, for example, helped him publish his article, but what really made him who he is in the history of science is the fact that the measurements showed him right.
Eugene Parker has received many accolades over his career, including the National Medal of Science for Physical Science and the title of S. Chandrasekhar Distinguished Service Professor Emeritus at the University of Chicago.
So in 1958, Gene Parker realized that the sun has a magnetic field and it will have a structure around the solar system that will be populated by what we call plasma. So these are hot particles that are flying from the sun all the way to the edge of the solar system. This is what he called the solar wind. So the solar wind is a structure generated by the sun, which basically envelops the whole of our solar system all the way to the edge. And it has been studied all the way to the edge of the solar system with, for example, the Voyager probes, which are now crossing into what's outside of the solar system, which is the furthest that man has ever been, or any man-made machines have ever reached across the solar system.
I laugh about this because I remember how upset some people were. They insisted I made a mathematical error, and I would reply, well, here you are. Here's 5 lines of algebra. You see I made a mistake. Show me. And it's amazing the number of people that just couldn't let go of the old ideas. They've been working on the spacecraft for several years, and one day the phone rang, and let's see, it was a guy that I know said, "We're talking about putting your name on the Solar Probe Plus," it was called. And did I object? And I sort of said, "No, I feel rather flattered." So he said, "Okay, that's what we'll do."
While the success of this mission bearing his name will not be known for many years to come, all the effort is sure to be worthwhile. The advances in engineering required to make this mission successful have been far-reaching and at times ingenious. That's because the speeds required to reach the Sun are mind-boggling in themselves.
The solar probe will be reaching the closest ever to the Sun and moving the fastest and reaching the hottest regions of the solar system. It's so fast that it could go from Chicago to Beijing in less than 1 minute.
There are many enabling technologies. The solar arrays were very important. The autonomy was very important. One of the ones that was obviously also critical is the heat shield, and developing the technology to actually protect the probe at the Sun.
The Parker Solar Probe is a technological marvel. The thermal protection system, the heat shield, will be glowing cherry red. The front surface of that will be 2,500 degrees Fahrenheit, while the spacecraft remains 85 degrees, roughly a warm day in Florida. The material sciences just didn't exist in the 60s and 70s. And so the carbon, which came out of, frankly, the military, looking for lightweight, stiff, strong structures, were the precursors to your tennis rackets and golf clubs, which are now the precursor to the carbon-carbon technologies that we have on Parker Solar Probe.
Temperatures so close to a star can reach a phenomenal range. Serious sun screening is required.
And a sandwich panel is a lot like a honeycomb panel you find in a traditional spacecraft or on airplanes. You have 2 outer face sheets, and then you have a core. In this case, the 2 outer face sheets are carbon-carbon composite, which is a lot like the graphite epoxy you might find in your golf clubs. It's just been superheated. And then the inside is a carbon foam. So the Parker Solar Probe heat shield has a white coating that's on the sun-facing surface of this giant frisbee that's protecting the rest of the spacecraft. And that white coating was specially designed here at the lab in collaboration with RED and the Space Department, as well as the Whiting School at Johns Hopkins proper, to actually work at the Sun. This was specifically designed for Solar Probe. And the concept is basically you'd rather be in a white car on a hot day than a black car on a hot day. It's just that it just knocks down the heat that much more. And so it's helping us stay cool at the Sun. That titanium truss was also specially designed for Solar Probe. It's actually a really neat piece. It's a welded titanium truss that's about 4 feet tall, but it only weighs about 50 pounds. And the key there is we're trying to minimize the conduction between the heat shield and the spacecraft. So you want to have as little stuff there as possible.
The hottest environments in the solar system will be probed by this mission, and its instruments that will be measuring all the different properties of the solar corona are protected by a shield, a state-of-the-art shield developed by NASA, which would make Captain America very envious. This shield keeps the instruments behind from being cooked every time the probe gets really close to the Sun. So the shield made of reinforced carbon is really something that is very recent technology, and only now we can actually get that close to the Sun and really verify some of the predictions that Gene Parker has made over his whole lifetime of trying to understand the solar wind.
Earlier iterations of this spacecraft design were predicated on a nuclear power supply. That idea was dropped in favor of solar panels, which brought their own design difficulties so close to the Sun.
Parker Solar Probe needs electrical energy to operate. Like any other satellite, or most other satellites, the spacecraft has solar arrays. But unlike other satellites, we have to generate electricity very close to the sun. For every watt of electrical energy we generate, we have to dissipate 13 watts of thermal energy. To do that, we need a cooling system, and we have a cooling system that's much like you'd find in your car. There are 2 water pumps in the system that pump water through the solar rays and up into radiators. Those radiators radiate the energy to deep space, which is very cold, as opposed to like a car where it would be radiated to air.
When we're at closest approach, the front surface of the heat shield will be at about 2,500 degrees Fahrenheit. The back surface of the heat shield will be about 600 degrees Fahrenheit. But then the spacecraft bus is basically sitting at 85 degrees Fahrenheit. So the shield is actually really keeping everything very cool. And that's most of the stuff is on the heat on the bus.
If you look at the science data, there's a big gap, and that gap is where Solar Probe is going. We're going to fill that gap of scientific knowledge. So it's true exploration. I mean, in that, and we're not following somebody. We're the first spacecraft, the first people to go there. So what'll be interesting is not the answers to the science questions. What'll be interesting is the new questions that Solar Probe forces us to ask. Because one thing we're pretty sure of is that probably have it somewhat wrong. Solar Probe will teach us what's right, and that'll generate many, many more questions and many more missions to come.
NASA's Parker Solar Probe will soon fly closer to the Sun than any spacecraft before it, some 4 million miles from the visible surface. But getting that close to the Sun requires some fancy orbital mechanics and a dash of brute force. Why is it so hard to get to the Sun?
Another reason Parker Solar Probe wasn't launched in the last 60 years is that getting so close to the Sun is hard. It takes a huge amount of energy to get to where we want to go. When a satellite lifts off the Earth, it carries the Earth's velocity around the solar system. So the Earth is moving at about 30 kilometers per second around the solar system.
Of all the space missions I've worked on, Parker Solar Probe is the most challenging and complex mission to design and to fly. The launch energy required to reach the Sun is 55 times of required to get to Mars and 2 times to Pluto.
Traveling so close to a star can also affect communications with Earth. In such a dangerous environment, engineers had to design software with serious smarts.
So Parker Solar Probe uses a sophisticated rule-based autonomy system to protect itself. For long periods of time, the spacecraft can't communicate to the Earth, and it needs to take care of itself. So the engineers during the development phase spent a lot of time thinking about what faults could affect Parker Solar Probe and came up with solutions for those faults. Those solutions are encoded in this rule-based autonomy system so that even if there's a fault on orbit, which of course we hope there isn't, the system can take care of itself. One of the most common questions I get are, what happens if the spacecraft gets hit by a solar flare or gets hit by a coronal mass ejection? Will it be destroyed? That's a very common question. And what I tell people is the science community will be elated if we were to get hit by a solar flare or a coronal mass ejection. They're very dramatic events when you look at them in a telescope or during an eclipse. But in the reality, they're very ethereal. The density of the particles isn't so high from the point where it could actually cause damage to the spacecraft. But the instruments aboard the spacecraft, the electromagnetic field instruments, the high-energy particle instruments, the plasma instruments, and the visible white light sensors will see this event. And how dramatic would that be to see a solar flare coming at you and fly right through it?
The sensor suite on board the Parker Solar Probe is indeed impressive. Each was designed to withstand the harsh radiation and temperatures to measure the particles, electric and magnetic fields of the solar wind. There is also an imaging instrument on the spacecraft called WISPER.
The WISPER instrument is the only imaging instrument on the Parker Solar Probe, and it is looking in the direction that the spacecraft is traveling. And what it sees is light scattered by the dust that's in orbit about the sun. But then, once we remove that, what we see is the light scattered by the electrons in the corona, in the solar wind. These measurements that we're making from the WSPR instrument have been made before by other instruments from 1 AU, from the distance of the Earth, about 100 million miles from the sun. By getting closer, we're increasing then the ability to see what's really close to the sun. The fact that you're close means that you don't have all this material that's in between you and the object that you're really interested in. And that contributes to background noise. And so you're looking at something that's much more pristine. You're looking at just that object all by itself.
We have 3 sensors that measure magnetic fields that are mounted on a boom behind the spacecraft in the shadow shield. And then we have 5 sensors that measure plasma voltage. These are electric field sensors. They extend into full sunlight and they get very hot. There are 2 ways to measure electric fields in space. One is using a technique that's called a double probe. Then there's another technique which is measuring plasma waves or radio waves. And Fields for the first time brings these 2 techniques together. I think the very first data that we get will be revolutionary. At first blush, it'll just be a bunch of numbers as a function of time. But the science team, will take those numbers and make visualizations in the form of spectrograms, and eventually those data will be related to models, and so we'll be able to compare directly 3D visual models of the coronal magnetic field. 2 of the key measurements to understanding coronal heating are the measurement of the magnetic field and the electric field, and together they give us what's called the Poynting flux, which is the energy flux of the corona. And to make those measurements, we have to actually go into that plasma and put sensors in the plasma to measure magnetic fields and electric fields directly, and that's what Fields will do. These measurements have never been made in the environment close to the sun. We've made measurements similar to this in the Earth's magnetosphere, Earth's ionosphere, but putting a package like this into the solar corona it's just never been done. The closest anyone's ever been to the sun, and based on what we've seen so far from spacecraft not quite as close, it's going to be striking and I think revolutionary.
The other science packages aboard Parker include SWEEP and ISIS, designed to study the particles emitted in the solar wind.
ISIS, the Integrated Science Investigation of the Sun, is an experiment which looks at energetic particles over a broad range of energies, from tens of thousands of electron volts up to about 100 million electron volts. The ISIS instrument is based on solid-state detectors. Those are detectors that when a particle passes through them, energy is deposited, and you can measure that energy and you can measure that the particle has actually passed through. So there's the solar wind, which is this continuous flow of lower energy particles. And then there are much more sporadic and episodic events like solar flares that spew out great numbers of these much more energetic particles. In our higher energy instrument, we have a whole set of layers of these detectors. And when a particle passes through those layers, it leaves energy in each and every one of those detectors. Those detectors are also segmented in pieces like a pie. And so when a particle comes through from a particular direction, you can tell both the direction the particle came through at, and you can tell the energy and species of that particle.
The SWEEP investigation consists of 3 separate instruments and a central electronics box. Most of the instruments within SWEEP sit on either side of the spacecraft, stare out over the entire sky, and make maps of all the different particles and what energies they're moving at, what types of particles they are. The purpose of SWEEP is to measure the bulk of the solar wind and the solar atmosphere. One of the biggest questions we want to resolve with Solar Probe is how the corona and the solar wind are heated. In order to do that, we need to see if there are waves that are coming from the sun and depositing energy within the solar atmosphere and in the solar wind. So we have a series of sensors across the spacecraft that will collect individual particles, electrons, fully ionized hydrogen and helium, which we call protons and alphas, and other minor ions, and make maps of the number of particles as a function of their speed and energy and type. We take those maps on the ground and we can interpret them to figure out the temperature, the density, the pressure of the solar wind and the solar atmosphere.
Learning the secrets of our star, the Sun, will help us understand the nature of the solar system and its all-embracing influence on our world. But the Parker Solar Probe is not the only mission destined for that star. The European Space Agency is also in the game. In collaboration with NASA, the Solar Orbiter is set to launch very soon and will be joining Parker in its quest for knowledge. The orbiter will fly an elliptical orbit within the orbit of Venus, but on a much greater inclination off the ecliptic, giving it access to the poles of the Sun. Unlike the Parker probe, the orbiter's main observation instruments will peer through the solar shield at a safe distance, then reconfigure when making a closer approach. Together, they will reveal the secrets of our closest star, the Sun. It won't be long now before you too can enjoy a view like this. Economy or business class? There will be a variety of choices of carrier and cabin. The view will be spectacular. This is the traditional way to orbit, a Russian Soyuz launched from Kazakhstan. NASA has to pay in the area of $70 million per seat return trip, and prices are about to go up. Only the Chinese have an alternative launch system. Very shortly, there will be 2 carriers taking tourists into space on suborbital flights. Blue Origin will probably launch first with their capsule and reusable launcher. Next will be Virgin Galactic and their suborbital space plane, launched from beneath a carrier aircraft and landing like one too, although to what altitude is still not known. Then you have America's return to space with its 2 commercial partners. Boeing have their CST Starliner, the first launch-capable capsule already off the assembly line. Looking every bit like an Apollo spacecraft, it will be able to ferry crew to and from the ISS. An unmanned test launch to the space station is imminent, and the crew has been picked to undertake the first few missions. Their standout competitors are SpaceX and their manned Dragon capsule, performing the same vital service. They're hedging their bets in the tourist sector as well, with their BFR concept naming their first paying customer.
Thank you, Elon. Thank you, everyone. Wow. I am from Japan. My name is Yusaku Maezawa. You can call me MZ, please.
After the success of the Falcon Heavy maiden launch, SpaceX is ramping up design and construction of its even larger rocket ship to Mars. However, the two other commercial entities aren't resting on their launchers either. Jeff Bezos' Blue Origin has developed its BE-4 engine to power an orbital delivery system, and they have the US Air Force on board. Not to be left out of the market, Virgin has also developed a small payload orbital system, Virgin Orbit with its Launcher 1. Flown to 35,000 feet, slung beneath Cosmic Girl, a Virgin 747, the two-stage rocket can lift up to 500 kilograms into orbit and an inclination up to 120 degrees. Dream Chaser is still in the running with its pilotless shuttle, still under development for long-duration orbits. The late Microsoft founder Paul Allen's company Stratolaunch has unveiled the largest aircraft in the world, a scaled-up airborne launch platform with multiple payloads from the existing Pegasus rocket to a medium and heavy launch vehicle and a reusable spaceplane in the future. In the meantime, there is no shortage of conventional launch systems competing for their share of the market. From the USA, Europe, China, India, Japan, even Israel and New Zealand. The key to any launch system is, of course, the engine. The smaller, lighter, and more powerful, the better. They pose many design problems. Fuel type, reignitable, chamber pressure limits, sea level or vacuum exhaust nozzle shape, but above all, reliability and cost. This is the Avio rocket factory in Colleferro, Italy. Here, engineers are developing the carbon fiber casing for the solid propellant rocket stages of ESA's new Vega-C launcher. To build them, 5,000 kilometers of carbon fiber impregnated with epoxy resin is wound around a pre-made metal mandrel. This produces the very lightweight but sturdy casings for the first, second and third stages of the Vega launcher. These casings are later fitted with an engine and loaded with solid propellant. One of these solid propulsion engines is the P120C. It was recently successfully tested in Kourou and is the largest and most powerful monolithic solid propulsion rocket ever built. With this new rocket, ESA hopes to respond to launcher market demands. The agency is also looking for value for money. This new engine is designed with the latest immersive technology and leading-edge materials and processes. Mass production will bring down the unit cost, but the design is for both Vega-C and the strap-on boosters for Ariane 6.
So certainly in the launcher sector, the competition is growing worldwide. But we believe that the European answer, the ESA answer with Vega-C and Ariane 6 is the right answer. In an aggressive manner, we are trying to make things more and more competitive. One of these examples is the joint solid rocket motor that we are developing across the two programs, the Vega-C and the Ariane 6, the P120C solid rocket motor that enables the possibility to harmonize resources and to have the same motor serving the Vega-C as a first stage as well as the Ariane 6 in both configuration as a strap-on boosters. So this is a very good answer to tackle the competitiveness aspect.
With Vega-C, the C stands for consolidation, ESA is further developing Vega. It will add increased performance to the flexibility of the current system without increasing the costs. Today, Vega can launch up to 1.5 tons on a 700-kilometer orbit. With Vega-C, it will go up to 2.3 tons. In order to increase performance, two new solid propulsion engines have been developed, the P120C and the Zefiro 40 for the second stage.
It is clear that whatever we develop has an exploitation objective. So we do not develop rockets just for the fun of it, but we develop rockets that need to be exploitable, therefore competitive in the worldwide market. And that's the way we are working hand in hand with industry to prepare them to walk on their legs in the future throughout the exploitation phase.
Further enhancements are made with Avom Plus, which is derived from the current Vega's Avom upper stage. Investing in new rocket motors also means investing in new launch facilities.
We have foreseen a lot of activities to modify the launch site from the Vega configuration to the Vega-C configuration. Vega-C is a heavy, larger and length launchers with respect to the Vega one. So for this reason we have to modify the hatches to the stages, increasing the diameters for what concerns the first stage.
Other changes include modified fluid services and installation of a more powerful crane needed to lift the heavier second stage of Vega-C. During these modifications, the site has to remain operational for the scheduled Vega launches. In the end, the launch site will be compatible with both launchers. With Vega-C, ESA is also working on related products such as the Space Rider, based on ESA's experimental re-entry vehicle IXV. It should allow for payloads to be sent into orbit and later return to Earth.
In addition to this, we have other products like a specific adapter for launching into orbit small spacecraft, so enabling the possibility of universities and research centers to access space at limited cost, so coping with the payloads which go from 1 kilogram up to 500 kilograms. We also have early elements of definition for a platform called Venus, which could allow payloads to transfer from orbit to orbit.
One unit which has been around for years and is still the Ferrari of rocket motors is the Space Shuttle main engine. Four of them will be mounted on the long-awaited Space Launch System. Reusing proven shuttle technology has saved time and money. The solid rocket boosters have been extended and tested. The Aerojet Rocketdyne RS-25 motors continue to roll off the assembly line. Fabrication of the immense components, cryogenic tanks, intertanks and fairings continues. The Orion capsule has flown once. The second flight-ready capsule is being prepared for the grand show. There is one more critical piece of kit required, perhaps one of the most important sections for keeping the astronauts alive, the service module. At Airbus in Europe, they have delivered the first flight-ready unit for the launch. The European component will house the electrical power, life support and propulsion unit for the Orion spacecraft, and like a giant pocket watch, every component is carefully and painstakingly assembled.
The European service module is part of an entire spacecraft built by an American company, Lockheed Martin, under the contract of NASA, and we are part of that. And of that spacecraft, NASA, Lockheed Martin is building. We are providing the European service module. We are providing the powerhouse of that entire spacecraft. That means we are providing the propulsion system, so the thrust to get into into the dedicated orbit we would like to fly with the spacecraft. We are providing the air condition, I'm saying. That's the thermal control system of the entire spacecraft. We take care of the heat, which has been generated in the capsule, which has been generated out of several electronic components in the European service module as well. And we are making sure that that heat gets radiated into the outside of that spacecraft. On top of this, we are generating power. Our solar array wings are producing that power. We are conditioning that power and deliver that to the crew module and deliver that to the batteries which are located inside the crew module. And finally, we are also providing what the astronaut need to have to live in that spacecraft. That's mainly water in terms of the consumables, and that's oxygen and nitrogen to generate the atmosphere in the crew module itself. On the power side, we are proud that we have installed hardware which has already been flown several years ago on a shuttle. So the big engine we are flying here, the OMS-E, was a challenge for us to bring that into the vehicle. This is not new technology in that sense, but the integration itself, that was really for us a challenge that was new. We're preparing ourselves to be ready for the final integration with the rest of the vehicle. And then we are ready for a test campaign in the US, which is including several environmental tests, several functional tests. That lasts a couple of months, up to that point where the NASA team is handing over the spacecraft to GSDO, to the launch campaign, so that the vehicle can be put onto the launcher, and then we are ready for flight.
The first engine is the big engine, which is coming from the space shuttle. With this big engine, we perform the big transition maneuver to go to the moon or to go back to the Earth. So we can see here the auxiliary thruster, which are red. We have 8 of them coming from Aerojet. Here we have the OMS-E, so the main engine, but without the nozzle, which will be integrated in one of the latest integration steps. We can see here the propellant tanks. We have 4 of them, 2 for each propellant.
ATV, basically the automated transport vehicle here in Europe, played a significant role in terms of opening the door for that specific joint work on that spacecraft. It also played a role that we learned our lessons with a kind of that service module. Finally, the components we have flown on ATV, there are not so many which we carry on in the Orion European Service Module. We have a couple of them, mainly auxiliary thrusters, yes, on the RCS thrusters, and also a couple of tanks like our pressure tanks, but there are not just a few items which we carry on from ATV into the European Service Module design.
The difficulty here for the human spaceflight is the change of mindset. So to think that we are here in this space mission, we are flying human, and it's not like a rocket which is only flying with a satellite. Therefore, we are putting more effort on the safety aspect. We have a lot of redundancy. Each change we introduce, the smallest change we introduce in our system has to go through the safety boards, our safety board, ESA safety board, and then the program safety board, to be sure that we can bring the crew back home safe.
With Orion and the service module certified, the sky won't be the limit. We will see ships refueling in orbit, a gateway station with a return to the Moon, then on to Mars and beyond. Opening space to industry and exploration, spaceflight will become the norm rather than the exception. Mining and manufacturing in orbit, power production, and habitats. One day, it might be as easy as driving to work in that red convertible of yours. Brute force at work. A European Ariane 5 rocket lifts off from Kourou. For Bepi-Colombo, Europe's first mission to Mercury, the real journey has begun. Its 7.5-year flight is a major challenge in orbital mechanics and will see it reach the smallest and innermost planet in our solar system in 2025. There, its discovery mission will really begin. A joint program with the Japanese space agency JAXA, Bepi-Colombo is one of the most complex scientific missions ever launched. It carries 2 orbiters designed to unravel many of Mercury's mysteries. These include an unusual magnetic field, strange surface features called hollows, and ancient ice hidden in polar craters.
One spacecraft is provided by ESA, which is MPO, we call it MPO, Mercury Planetary Orbiter. And this spacecraft has a focus more on the planet. We want to observe the planet, do remote sensing, characterize the surface, count the craters, wanting to know about the composition of the surface, the interior of that planet. And in addition, we have a second spacecraft, and this spacecraft is called the Mercury Magnetospheric Orbiter, more focused on the environment, and this spacecraft is provided by the Japanese Space Agency.
We know the Mercury is very hot, and we have to make the satellite that can survive in that harsh environment. And we know, well, it is very difficult, and when we started, we already some development, and we think that we can do it. But actually, the hurdle is much harder than we expected, and takes a long time. But now, you see, this is the flight model.
Bepi-Colombo's road, design, research and development phase, the construction, assembly and testing phase, has been long and hard, culminating in the launch from the European spaceport in French Guiana.
Mercury is 3 times closer to the Sun, and therefore the radiation or the heat which we are getting from Mercury is 10 times higher.
So everything which we had to develop had to withstand the higher temperatures, but also the higher radiation doses which we got from the solar wind. And for that we need special insulation of our spacecraft, special materials to be developed for the antenna, for the solar panels. And that was a very big challenge for the mission in itself.
Now, of course, we do the health checks to verify the system is healthy. And we did alignment, mechanical checks, electrical checks all over. We checked the propulsion subsystems to see if the propulsion elements are still leak tight in preparation for the fueling.
Hardware apart, training of the scientists and technicians back on Earth was extensive, requiring years of preparation.
The simulations campaign is the first time that all the experts involved in the Bepi-Colombo spacecraft design, integration, testing and operations work together as a single team. The campaign is essential for this group to learn to work as a single team, to train the decision-making process. The campaign is also very important for us to fine-tune our plans and procedures. It's the first time that we exercise the flight plans and procedures in a realistic context, taking into account communication constraints, ground station, and timing.
In preparing for a mission like this, we have to carefully train all the aspects. What we actually do in the rehearsal we do in preparation of a launch, we train the teams to work together, we train the teams to work with the flight procedures, and also we train the teams as much as we can in flight conditions. So normally when we test before, we test with many workarounds. What we try to simulate here is actually to replicate as much as possible flight condition, and we typically do between 20 and 30 of these rehearsals before a flight.
With the nail-biting launch sequence complete, for many it's time to sit back and wait.
The cruise will be a bit above 7 years. We will fly by once the Earth, 2 times Venus and 6 times Mercury itself, before we come into the orbit, which allows us to capture with the small gravity of planet Mercury against the big sun. That means when we fly, we constantly brake against the sun because we fly into the inner side of our solar system. And when you fly towards the most heaviest element there, you constantly accelerate. We don't want that. That's why we decelerate.
Because this planet is so close to the sun, you need to have a lot of energy to go there. It's even easier to send a spacecraft to Pluto than to Mercury. You have to brake until the gravity of the sun, and you need a lot of energy. And for that reason, our mission takes quite a long time because we also need the help of planetary flybys in order to bring our spacecraft there. Then we want to send 2 spacecraft in an orbit around Mercury, and that in itself is also a problem because on the other hand you need to brake against the sun, but on the other hand you also need to accelerate your spacecraft to bring it in the same speed as Mercury goes around the sun, and then to finally drop it into an orbit of the planet. I'm working now 14 years on this mission, so it's really like a baby growing up and then leaving the house finally. So for me, it's a special moment.
Bepi-Colombo's main component parts are 2 orbiters and 1 transfer module. These took 4 weeks to disassemble and pack and required 70 shipping containers and 4 cargo planes to ensure safe delivery to the European spaceport at Kourou. Spacecraft have got up close and personal with Mercury twice before, thanks to NASA's Mariner 10 probe and, some 40 years later, the Messenger mission. Messenger mapped the surface and identified strong evidence for water ice in shaded craters. But its mission also raised new questions about this mysterious planet. This latest probe has a sophisticated suite of sensors and instruments that will come into play when it reaches orbit around Mercury.
So the big step forward for Bepi-Colombo is the fact that we have two spacecraft, the European Space Agency spacecraft, which is looking directly designed to look at the surface of the planet and to study the planet in detail. And the orbit is designed such that you maximise the objectives that you can do relating to the surface. And the second spacecraft is designed to look at the environment. And so having two spacecraft will enable us to do a great deal of new science compared to the previous missions.
With Bepi-Colombo, with a two-satellite approach, we have one satellite, the MMO, sitting in the solar wind, and the other one is inside the magnetosphere, so we can see what is coming towards the magnetosphere and what is driving changes within the magnetosphere.
We have 11 instruments on board the spacecraft, and when we are at Mercury, these instruments are gathering data, and then they will store it in effectively a large hard drive, which we have on board the spacecraft. That data is then collected over a number of hours, and when we have a visibility with the spacecraft in Mercury, typically it's every 16 hours we can talk to the spacecraft at Mercury. The data is then downlinked using a very large high-gain antenna. It's a very powerful antenna in order to have a data rate of about 340 kilobits per second. If you compare it to your home internet, this is nothing. It's a very slow data rate, but it's very fast considering we are very close to the sun and we might get some interference from the energy from the sun. So it's as powerful as we can have with the resources we have on board the spacecraft.
With the assistance of gravity flybys, the spacecraft will rely on its solar electric propulsion system. It consists of 4 TX ion thrusters, fueled with xenon gas that is ionized and electrically propelled out, providing thrust for months at a time. The thrusters will rely on the spacecraft's solar arrays for power. The T6 thrusters can accelerate Bepi-Colombo 15 times more efficiently than a conventional chemical thruster.
So at Earth, the solar flux is 1.4, more or less 1.4 kilowatts per square meter. As we approach Mercury, which is the most innermost planet of the solar system, that solar flux has risen 10 times. So now we have 14 kilowatts per square meter. Now you might think that's a good thing in the sense that it gives you more energy to turn into electricity to be able to run your thrusters. But it turns out that that immense flux that we're getting from the sun also drives the temperature of the spacecraft very high. And in particular, our solar arrays, which are sensitive to high temperature, need to be protected. Now, we do that in a number of different ways. We keep as much of the open surface covered in little mirrors that we call OSRs, optical surface reflectors, or with specially developed white coatings, which help to reject the heat from the sun. But perhaps the biggest mechanism that we use to keep the solar array cool is to off-point. Rather than pointing the solar rays directly to the sun, we point them at a very shallow angle. And what that does is it means it keeps the thermal energies under control while still giving us the necessary energy to turn into electric power for the thrusters. Now, the reason why the solar rays are so big is because we're off-pointing by so much that in order to get a sufficient cross-section of the solar array needs to be big.
Protected by multi-layered insulation, hand-stitched thermal blankets and a radiator to dissipate heat, ESA's Mercury planetary orbiter will have to cope with extreme environments.
If a unit is getting too hot, if one of the payloads is getting too hot, in order to stop that payload from being damaged, we'll switch it off will send an emergency message back to the Earth, reporting that there's an issue. We need ESOC to take action to investigate why items are getting too hot, and then to recover the unit and the spacecraft.
Once they reach Mercury in late 2025, the orbiters will separate from the transfer module to begin their comprehensive scientific mission in 2026.
In principle, all the planets have the same chemical elements because the whole solar system has the same chemical composition, but it's distributed differently in different planets and different environments. So it's vital to understand what is the ratio of the abundances of different elements to understand the structure of the surface of Mercury.
One of the advanced sensors aboard Bepi-Colombo is a sensitive imaging X-ray spectrometer called MIX, which produces a global map of Mercury's surface atomic composition at high spatial resolution.
The MIX instrument, the Mercury imaging X-ray spectrometer, looks at the fluorescence that happens when the sun shines on Mercury in X-rays. So it's a bit like when you wear a shirt in party lights which has been washed in the right sort of washing powder. The party lights shine on your shirt glows. And it's exactly the same with the sun and Mercury. The sun shines on the surface in X-rays, and the surface of Mercury glows in X-rays. And if you detect those X-rays, you can tell what Mercury is made of. And what it tells you, you're actually counting the atoms on the surface. So it tells you in a very quantitative way exactly what the surface layer of Mercury is made of.
So I would say one of the most exciting things about MIX is the fact that we will be able to produce the first images in X-ray wavelengths of Mercury's surface, and that is going to be able to give us a great deal of new information, both on a global scale and on a local scale, of how the composition of Mercury varies over its entirety of its surface. Another aspect of the MIX science which I'm personally very excited about is the fact that we can also see X-rays from the surface which are being produced by particles from Mercury's magnetosphere actually precipitating onto the surface and producing X-rays that we will be able to also measure. So we can have an extra aspect to the science that we can do relating to how Mercury's magnetosphere interacts with the surface.
Among the mysteries revealed by MESSENGER are irregularly shaped depressions known as hollows, found in clusters over a wide range of latitudes and longitudes. These hollows have bright interiors and halos with a fresh appearance that suggests they are geologically very young.
I think that there are two mystery or two very intriguing objectives of Bepi-Colombo. The first one are the hollows. The hollows are features discovered by MESSENGER. These features seem to be quite distributed all over the surface of Mercury, and is something related to the volatile that come to the surface after an impact, after a volcanic event. But of course we need Bepi-Colombo to really characterize and to understand which is the origin of the hollows.
There are also clear traces of much more recent hollows where the surface has been eaten away by some process that removed solid volatile substances, such as sulfur, chlorine, sodium and potassium, as vapor.
And this is because we don't have the composition data. We can measure the dimension, the size of the hollows, we can have an idea of the distribution, but no more. And also, of course, Messenger didn't get so many high-resolution images, and didn't have the digital terrain model, the 3D images at high resolution, as we will provide with Symbiosis. In other words, I think that the hollows are one of the most interesting discoveries made by Messenger.
Existing evidence indicates that if combined and spread out over a city the size of, say, Washington, the amount of water ice concealed in Mercury's polar craters would be over 2 miles thick.
And the second point is the water, because even Messenger said, yes, on the polar region we may have some water ice, hidden just in the shadow of the craters, because in the polar region there are some floor of the craters, some wall of the craters that are always in shadow, as occur on the Moon. But the Messenger didn't have the instrument to observe if it is, to make a direct measurement of water, as occurred on the Moon. And Bepi-Colombo and Symbiosis will be able to do it with our spectrograph.
If confirmed by Bepi-Colombo, the story of how the inner planets, including Earth, acquired water and some of the chemical building blocks for life becomes much clearer. It would support the theory that organic compounds, as well as water, were delivered from the outer solar system to the inner planets and may have led to prebiotic chemical synthesis and, as a consequence, life on Earth.
So studying Mercury is crucial to better understand the formation of our solar system, how Earth is formed and evolved, and where we are coming from. So Mercury is in a way a missing piece in the big puzzle of the formation of the solar system, and a crucial end member because it's close to the Sun, and if you want to get this full picture you have to look at the planet close to the Sun, as we also did in past missions that we were looking at the comets or planets further out.
We all have our individual science objectives for each of our instruments, and what we're starting to do now is to bring all of our ideas together, which obviously are complementary to each other, and we can start to form a broader set of goals at working group level, so the surface working group and the environment working group. And that helps us to, again, maximise the science that we can get from the mission by coordinating what it is that we want to do, potentially looking at specific targets on the surface and that kind of thing. We can work together to get the best from the mission that we possibly can.
ESA science and engineering teams have already been working on Bepi-Colombo for more than a decade. But with a long journey ahead of it, the recent launch marks only the beginning of the next intriguing stage of Bepi-Colombo's voyage of discovery. The building blocks of the solar system are quickly giving up their secrets. 2 major missions are underway. The NASA OSIRIS-REx, which is now closing in on its target asteroid Bennu, and the JAXA mission Hyabusa 2 to Ryugu, which is well into its observation leg of the mission, studying the asteroid up close. Both missions hope to return samples to Earth for a more complete study. A 3.5-year journey to asteroid Ryugu is over, and the Hyabusa 2 science mission begins. Ryugu, part of the Apollo group, is potentially a threat to Earth in the years to come. It's an unusual asteroid, a CG type, meaning it has qualities of both C-type and G-type carbonaceous asteroids. It is just under a kilometer in diameter and fast-moving. As part of its payload, Hyabusa 2 has several deployable landers, 2 Minerva IIs, the Franco-German mascot lander, and target acquisition markers for the touchdown.
Okay, we want to see the boulders. We have a chance to see the boulders in a vertical structure. We also see the crack in the boulders. There is also regolith. We know from the spectral information we have so far that there is something a little bit redder, something a little bit bluer on the surface. So that's very interesting because there are differences on the surface. We have the feeling that the bluer, it may be a little bit fresher than redder. And that basically gives us a good idea of the history of the material on the surface. And of course, there are a number of landing sites which are red and blue, or which have red and blue in it, and that's probably preferred, at least for the camera, so we have a chance to see both of the surface units.
From the feedback I have obtained now from our principal investigators of the instruments seems to be that it's a very interesting asteroid and that there are several aspects which is covering the science objective of each instrument.
First to be deployed to the asteroid were 2 Minerva probes. These rovers are based on the original Minerva craft flown on Hyabusa 1, which unfortunately failed to land on their target asteroid. These ones, however, were successful. They have radioed back several stunning photographs from the surface of the asteroid, including this sequence of the Sun crossing the skyline as the asteroid tumbles.
Asteroid missions are very important and very interesting from the scientific point of view because it is believed that asteroids and comets are bringing water to the Earth in the very early phase of the development of the Earth. And with this water and also organic materials, it is believed that life on Earth has developed. And very importantly is also there to understand the evolution of the solar system, because asteroids are supposed to be building blocks of our early solar system.
The Hyabusa 2 mission has been years in the making. As with any deep space probe, years are spent on the drawing board developing the hardware and software. Then come years of construction and extensive testing. The aim of the Hyabusa 2 mission is to learn more about the origin and evolution of the solar system. As asteroids account for some of the most primordial celestial bodies, researching them gives us a glimpse into our cosmic past. Scientists are keen to learn more about the properties and structure of near-Earth asteroids in order to gain new insights into how our solar system formed and how water and life emerged on Earth. It's an audacious mission.
I mean, they're flying to an asteroid. Now we map the asteroid. Then a lander will be deployed like Mascot or Minerva. They're trying to do 3 samples, and then they have also explosive on board to produce a crater on the surface of in the asteroid. I mean, this is, to me, it's a unique mission they are doing, and we are part of it. So I'm really proud of it.
And of course, we are interested in the geology, the geomorphology, the structure, the size of the big boulders, and also the structure of the regolith, and giving some hints of the evolution of the surface, of the forming and evolution of the surface of Ryugu. Oh, I think for a camera, all of the rendering sites are quite okay. So the most interesting thing is to see the big boulders from the vertical structure. We really can look how deep they are in the surface. And there are many boulders on Ryugu, so I'm pretty sure we get a good view of this interesting part of this asteroid.
The second batch of asteroid landers developed by the German and French space organizations were launched and, after a short freefall, successfully landed at the southern hemisphere of asteroid Ryugu. After bouncing several times on the rock-strewn surface, the 2 landers have begun their scientific research.
And you know that Mascot is made to bounce. That makes it robust, but it also means that the final resting location is not exactly possible to calculate it. So there's a dispersion of possible sites, and there is some variation in between. There could be, among these many possibilities, some bad ones, and we have to go to places where the chance to hit a good one is highest, but does not exclude that we end up in a bad one.
Autonomous handling doesn't mean that Mascot is doing everything as he likes to, so there's lots of sequences and command stacks behind, which are carefully tested and planned. So the robustness of these sequences have to be tested against all these different conditions we can meet on the asteroid. So if we bounce or land more in the west or more in the east, for this, the input Mascot has, which he uses for his autonomously, this is really carefully planned and tested, and so there's all the work in, and I think we did a very well job, and so I'm relaxed.
With its 4 instruments, including the micromega spectrometer developed by the IAS Space Astrophysics Institute at Orsay with CNES oversight, Mascot is set to analyze the mineral composition of grains in the asteroid's soil in an attempt to unlock its secrets at 2 sites just a few meters apart. They also took some fascinating images.
I think at least for me, the most important question is the big number of boulders. Where did they come from? Why has this asteroid so many boulders? Why are these boulders to some extent covered by the surface, so they are in the subsurface? And the question here is, what are the source of the boulders? Are they from the interior or coming from outside? Are they a relic from some kind of collision from a bigger body, where Ryugu is now a relictic part of it? So I think that's the most important question.
Mascot was operational for over 17 hours, during which it collected data from the asteroid's surface and transmitted it back to Hyabusa 2 overhead, which relayed the data back to Earth. The next probe to be released is the 3rd Minerva robot, the largest of the Minervas.
I would like just to express again this amazing work which the whole team has done, DLR as well as CNES, as well as JAXA, surely. This was a very good example of a very good collaboration on an international level, and I hope that it will go on in the future.
GNC that has to tell the autonomy manager if we are on the right side or which side we should turn to upright.
For France, this was a big expectation.
The entire mission has been a close collaboration between nations. Japanese, German and French scientists and engineers have enjoyed over a decade of scientific cooperation, even if there are language barriers.
Realistic delivery with 6 slots in which the mascot...
I like it because it's a small mission with little overhead, and it's very nice to work with the Japanese because they are very success-oriented. They are willing to take risks. They have also, because of language issues, much less paperwork than NASA or ESA does. So most things are done in discussions, and you agree on something, you look into your eyes and say, yes, we do this, yes, and you rely on the words. You don't sign big papers. And that's something I like because it makes work so much easier and smoother and quicker.
Oh yes, the mission is very good. There are, in all the teams from Hyabusa mascot, there are very excellent engineers and also very excellent scientists. So I'm really confident and excited. That's the first time we do this.
The Hyabusa 2 mission is very interesting from the point of view because Hyabusa 2 is investigating a C-type asteroid. Ryugu is a very primitive asteroid which is supposed to have organic material on the surface. In addition, Hyabusa 2 has got in situ science provided by the Mascot lander and also 2 to 3 further small Minerva landers, and it will bring some samples back to Earth so that we can investigate it then on Earth in the labs.
In the spirit of friendly competition, NASA was quick to congratulate JAXA for reaching their asteroid first.
This is Dante Loretta, leader of the NASA OSIRIS-REx asteroid sample return mission, congratulating you on the successful approach to asteroid Ryugu. We're all very proud of your amazing accomplishments so far, and we look forward to working with you together over the next year to maximize the scientific return from our 2 missions.
NASA's OSIRIS-REx probe is about to reach its target, Bennu, another CG-type asteroid close to Earth's orbit. A less ambitious mission, OSIRIS-REx will touch down and retrieve a surface sample, then return it to Earth.
Oh, asteroids are very interesting objects. So they are very primary. They are the fundamental things, the fundamental material of the solar system. And on the other hand, they have, to some extent, they cross the orbit of the Earth. They are dangerous. And just to know their structure, composition will help in order to avoid collision with the Earth if this may happen. And that will give us enough information in order to really find a way to mitigate this kind of catastrophic future.
And there is no shortage of conceivably dangerous asteroids out there.
It's one of the main points, of course, yeah, because we really cannot exclude it, but it's on a long time scale. But in any case, we know from the past, and we know from the past 4 billion years, that this is a real danger for planets.
"66 million years ago, one asteroid measuring 10 kilometers across completely changed Earth's climate, wiping out 2/3 of living species and consigning the dinosaurs to history books and museum displays. Fortunately, large asteroid strikes are very rare, but smaller ones can still be dangerous. Along with other organizations across the world, ESA is working hard to identify and track them.
We currently have a detection rate of something like 200 asteroids per month, and maybe 3, 4, 5 of them are objects which might hit the Earth. So currently we have 740 objects where we don't know if they will hit the Earth or not. There's none which is really a serious threat, which we currently know of. There's plenty of things out there which we have not yet detected, which we are still searching for, but from what we know right now, there's nothing which we have to really worry about. What we are worried is if a 20-meter object would approach. That was the case 5 years ago in Chelyabinsk, when a 20-meter object exploded over a city in Russia, and 1,500 people went to hospital because they were close to a window or they were hit by fragments, and they were not aware, nobody knew that this object would come. And this is what we could improve in the future, that our telescope would detect this a week maybe in advance.
ESA's new Fly-Eye telescope will conduct automated nightly sky surveys. It works by splitting the image into 16 smaller sub-images, greatly expanding the field of view.
We plan our Fly-Eye telescope in Sicily. We can scan the sky within 48 hours. So whenever an object bigger than 10-15 meters would approach, we should be able to see it beforehand, and then we would pass this information to the authorities.
Currently, the first Fly-Eye telescope is foreseen to be placed in Sicily, near the Monte Mufara. There are other 3 telescopes foreseen in the frame of the next project, and there are many advantages in having 4 identical telescopes, both placed in northern and southern hemisphere. The coverage of the both hemispheres is due to geometric reason, in order to cover the full celestial sphere. Then, considering that the telescope needs a clear sky for the observation, doubling the number of telescopes allows to compensate in case of bad weather conditions.
ESA's Fly-Eye telescope will improve our chances of detecting these potentially dangerous objects, while the asteroid missions will increase our knowledge of asteroids and look at ways of protecting our planet. The telescope was designed and built by a consortium of companies from Italy, Poland and Romania.
The Fly-Eye telescope is based on a novel and original optical architecture that mimics, as the name says, the eye of the insects. In practice, it is composed by 16 independent and single telescopes that share a common primary mirror. This way we can join together different optical features that are difficult to combine together in a single telescope. And every single optical channel, every single telescope that composes the Fly-Eye telescope is provided with a focal plane which already provides a large field of view. The combination of the 16 field of views creates a very huge field of view. In practice, we have for each single telescope 2.75 square degrees of field of view that multiplied by 16 gives the 44th field of view of the overall instrument. This is very important due to the fact that with such a large field of view you can map large areas of the sky very quickly, and you can this way scan the full visible sky at least 3 times per night. A typical observation of the telescope is about 60 seconds exposure time. During this time, of course, the structure must be very stiff in order to avoid the vibration that could blur the image and diminish the possibility of the telescope to look for faint objects. And this is very important from the optical point of view due to the fact that all the performances that are collected together in the telescope must be maintained also from a mechanical point of view.
Fly-Eye telescope, due to its large field of view and also the capability to quick scan the sky, allow to arrive up to 3 complete scanning of the sky per night. This feature allows to implement what we call a wide survey. What it exists today is what is called the deep survey, so a specific observation of an asteroid very far, but today we think we are the first, we are offering a service to cover all the world, because we can inform the population with a week in advance that an asteroid can hit to the Earth, so we can protect the population. This instrument can detect an object like a tennis ball at an orbit 1,000 kilometers, moving at 10 kilometers per second. After 10 detection, we can calculate the orbit with an accuracy of 20 meters along a track. So are important feature, and we can implement a really cooperative way between radar and optical.
ESA is currently working on a set of space safety and security activities, which focus on threats such as space weather, artificial debris, and asteroids. By enhancing the existing space situational awareness program, these will help us better understand the risks to our planet and prevent disaster.
Searching for asteroids and mitigating the risk of impacts, while at the same time collaborating with international partners. That's how I see how ESA can contribute to fulfill UN Sustainable Development Goals.
All going well, the Hyabusa 2 sample will land in the Australian outback sometime in 2020. OSIRIS-REx will follow with a sample for return in 2023. Gaia launched in December 2013. Its 5-year mission to study the billions of stars in our Milky Way galaxy. Its first data release covered a mere 1 billion stars and the distance and motions for just 2 million. Now its second data release has updated this to an extraordinary 1.7 billion stars. The second data release of ESA's Gaia mission has produced an extraordinary catalogue of over 1.5 billion stars in our galaxy. Based on observations between July 2014 and May 2016, it includes the most accurate information yet on the positions, brightness, distance, motion, color, and temperature of stars in the Milky Way, as well as information on asteroids and quasars.
The data comes down to the ESA antennas on the Asteroid network in Argentina, in Spain, and in Australia. From there, it goes to Darmstadt, who control the spacecraft, and then it goes to our central data processing hub near Madrid in Spain, which is an ESA center. And from there, it goes to the data processing consortium, which then slices it up in different parts and processes this into science products.
This new image, showing the distribution of stars in the Milky Way, represents 22 months of observations. 1.7 billion stars, their distance, motions, and color. The dark areas are not empty. They contain interstellar gas and dust.
So Gaia is measuring with 3 different instruments. It is doing astrometry, photometry, and spectroscopy. So astrometry is measuring the positions, which helps to get the distances and also the motion of the stars. Photometry is essentially getting the color of the star, and color gives us the temperature of the star.
This stunning new image was produced by recording the color from stars and combining it with their overall brightness. We now know the position and brightness of 1.7 billion stars. Importantly, as well as the color, we also know the distance and proper motion of 1.3 billion stars, plus the surface temperature of 161 million, the radius and luminosity of 77 million, and the radial velocity of 7 million stars.
With spectroscopy, we are using one element which is based on Doppler effect. We are looking how the lines on the spectra are moving, and we get the speed of the star on the line of sight. But spectroscopy can be also used to analyze better the stars. So it is really the combination of all these elements. We know where the stars are, how they are moving, what is their temperature, and what are the properties of these stars. The most eagerly awaited result from Gaia are so-called parallaxes, which is the measurement which gives a handle to the distance of the stars. And this is a very tough measurement to be done. And we have known since Hipparchus, the previous ESA mission, distances to about 100,000 stars. And Gaia is going to increase that number to above 1 billion. So that is a real revolution.
The raw data from Gaia is used to create stunning visuals and animations. Obtaining the parallax measurement involved determining the apparent motion of the star by using 2 different vantage points along the Earth's orbit around the Sun, and separating it from the star's true motion through the galaxy. To do this, the spacecraft is orbiting around the L2 Lagrange point. The Sun, the Earth, and the Moon are all roughly in one direction, and the sum of gravitational forces makes it an ideal position to study the stars at the dark side of the sky. Closer to home, Gaia observed 14,000 known solar system objects too, mainly asteroids. The quality of data provides us pinpoint accuracy over time of these orbiting neighbors.
So we have a multitude of targets. We have solar system objects, asteroids. Most of them are stars, but we also see external galaxies and quasars. And it is really different kind of science what you can get out from this. From the solar system targets, we can measure their positions extremely accurately. We will know much better than ever before the orbits of asteroids, for example. Stars we are using to understand our Milky Way better. From stars we get really the structure of our galaxy. And the advantage of seeing some quasars is that the reference system of coordinates is based on quasars because they are far away so they don't move. And we can observe them in radio. And now finally with Gaia we can see the same objects in optical wavelengths. So we can tie radio reference system to optical one.
This animation of our own galaxy, the Milky Way, shows the roughly 100 billion stars. The location of the Earth's sun is shown here in one of the spiral arms. The Hipparchus survey is in red. It pinpointed the positions of more than 100,000 stars to a high precision. Gaia has surveyed up to 30,000 light years in all directions, encompassing 1.5 billion stars. Galaxies come in all shapes and sizes. Only one of them is our home. Gaia is opening up our part of the galaxy to help us understand the past, present, and future of our region of space. The first data release already produced hundreds of scientific results, but for astronomers across the world, the best is yet to come.
Essential thing of the Gaia mission is that the surprises will come later, because we make the catalog, and it is the scientists in the community who are going to utilize it and give the scientific surprises to us.
The Gaia mission is expected to be extended to 2020, which means not only cataloging more stars, but also examining possible exoplanets around them and even more surprises. A SpaceX Falcon 9 is ready for launch. The Falcon 9 rocket has proven its ability and reliability and become one of NASA's go-to launchers.
0. Liftoff. The SpaceX Falcon 9 carrying TESS, a planet-hunting spacecraft that will search for new worlds beyond our solar system.
Its payload is TESS, the Transiting Exoplanet Survey Satellite, NASA's newest exoplanet mission, led by MIT. It will find thousands of new planets orbiting nearby stars.
And visual confirmation as well of the fairing separation.
Grid set deployed.
TESS will eventually fly in a special, highly elliptical orbit that maximizes the amount of sky the spacecraft can image. It will expand its orbit until it can get a gravitational assist from the Moon. This slingshot will move it into a stable orbit that is tipped at about 40 degrees from the Moon's orbital plane. TESS will orbit Earth in exactly half the time it takes the Moon to orbit once. This feature helps stabilize the spacecraft against tugs from the Moon's gravity. The telescope will then spend most of its 13.7-day orbit observing the sky. As it nears Earth, it will rotate and transmit all its accumulated data to scientists on the ground. Over its 2-year mission, TESS will observe nearly the entire sky and potentially find thousands of new exoplanets.
TESS, the Transiting Exoplanet Survey Satellite, is NASA's newest exoplanet mission. It's being led out of MIT, and it's going to find thousands of new planets orbiting bright nearby stars. And it's going to build upon the legacy of the Kepler mission, only it's going to focus on nearby bright stars that are sprinkled across the whole sky, and it's going to help us answer a really important question, and that is, which of our near-stellar neighbors has planets?
In those 2 years, TESS will look for signs of planets ranging from Earth-size to giants larger than Jupiter. TESS will search for these new worlds or exoplanets using transits, the same method as the Kepler mission. As a planet passes in front of its star, it blocks some of the light, causing a slight drop in brightness. TAS can detect these subtle dips and even use them to determine some basic features of the planets, such as their size and orbit.
The coverage of the TESS cameras is unprecedented in terms of the amount of sky that they can actually see at any given time, and also their ability to cover such a broad portion of the sky. The types of targets that TESS will allow us to find will enclose essentially all of the bright nearby stars.
Each of TESS's cameras has a 16.8 megapixel sensor covering a 24-degree square large enough to contain an entire constellation. TESS will watch each observation sector for about 27 days before rotating to the next one, covering first the south and then the north, to eventually build a map of 85% of the sky.
The thing that we're really excited about with TESS is the way that it'll actually build on the momentum that we started with Kepler. So TESS is going to take that same search approach but apply it to the vast majority of the sky, which still hasn't really been looked at in detail when searching for exoplanets. And by focusing especially on planets that orbit bright nearby stars, TESS allows us to start looking at things like planet composition and atmospheric makeup. And that'll then be crucial when we want to start looking around stars that are even further away and in deeper parts of the galaxy as well.
This coverage, about 350 times what Kepler first observed, will make TESS the first exoplanet mission to survey almost the entire sky. TESS is the vanguard of a new era of exoplanet study and will forever expand our understanding of worlds beyond our own. The space telescope Cheops, characterizing exoplanet satellite, is ESA's follow-up mission. The telescope will study hundreds of known exoplanets using the transit method, measuring the dip in light as a planet transits its parent star.
When the planet goes in front of the disk of the star, then the light that we receive from the star decreases, right? And so this is what we want to measure, how much this light decreases when the planet goes in front of the star. And this is what's called the transit method.
Hundreds of known planets orbiting stars outside our solar system will soon be under scrutiny by Cheops.
We want to know what these planets are made of. We want to know how hot they are. We want to know the atmospheric composition, structure. We want to know the surface temperature. We want to know if there's water there, and eventually if there's life.
This is the Cheops instrument in a clean room at the University of Bern, where it was built, assembled and tested using electrical and optical ground support equipment and a thermal vacuum chamber. Cheops will measure the minute dip in light from a star when a planet transits across it. The size of the dip provides a direct measure of the ratio of the size of the planet and the star. This, combined with a knowledge of the size of the star, gives the planet's size. Radial velocity measurements from ground observatories will supply its mass.
When you have the mass and the radius, you have two very important things about an object, because you can get what we call the mean density after that. And that can give you a lot of information about the composition of a planet. For example, it can immediately tell you whether the planet is mainly formed of gas or if it's a rocky planet.
The telescope houses two mirrors, a CCD detector or camera, and a baffle to reduce stray light.
What makes Cheops unique, it's the only follow-up mission. So we are not aiming at discovering new planet. We're just aiming at going back to the ones we know and measure their size, either for the first time because it hasn't been measured yet, or improve the measurement that have been done in the past, either from the ground or from a space telescope with less precision.
The challenge was to build an extremely accurate and stable telescope that blocked signals caused by stray light from its electronics and instruments. The telescope will therefore be kept at -10 degrees Celsius and the detector at -40 degrees to reduce signal noise. The Cheops science team is currently selecting the best target exoplanets for further study. Other scientists will also be invited to submit proposals to use the Space Telescope. Now in Madrid for further launch preparations, launched from ESA's facilities aboard a Soyuz rocket, the Cheops will begin a new era of discovery. A recent analysis of 6 years of data from the MOA-2 ground-based survey concludes that exoplanets similar to Neptune in mass and probably composition are likely the most common worlds in the outer reaches of planetary systems. This data was achieved by a technique called microlensing. When a star passes directly between us and a more distant star, its gravity can act like a lens, magnifying the background star's brightness significantly for a few weeks. If the lensing star hosts a planet, the planet's gravity can produce a noticeable change in brightness over hours or days. This spike signals not only the planet's presence, but tells us its mass and distance from the star. Each method of finding exoplanets has different strengths. Radial velocity measurements reveal planets by detecting how they cause the star to move. Transit measurements reveal dips in starlight caused by planets passing in front of their stars. Both work best for massive planets in close orbits, and for stars up to hundreds of light years away. Microlensing opens a planetary window onto a larger part of the galaxy, reaching thousands of light years. And because microlensing is more sensitive to smaller planets farther from their stars, it can reveal new planetary populations. In the MOA-2 study, researchers discovered that planets beyond a certain distance from their star tend to be roughly 20 Earth masses, or about the same as Neptune. That distance is what astronomers call the snow line, where water would be frozen during the formation of a planetary system. For our system, that location is roughly 2.7 times farther from the Sun than Earth. Beyond the snow line, where there is more solid material to coagulate and initiate the planet formation process, planetary formation is thought to be most efficient. In fact, worlds formed in this frozen hinterland may play an important role in making habitable planets closer to their star. The gravity of planets beyond the snow line can help send water-rich asteroids inward, where they can deliver water to young rocky worlds. To validate this theory, you need a space-based telescope with some unique properties. NASA's new telescope, WFIRST, is the Wide Field Infrared Survey Telescope.
Telescopes generally come into two different flavors. You have really powerful big telescopes, but those telescopes see a tiny part of the sky. Or telescopes are smaller, and so they lack that power, but they can see big parts of the sky. WFIRST is the best of both worlds.
WFIRST is the Wide Field Infrared Survey Telescope. What I think of WFIRST is doing is building on what were the two great successes astronomically of the 1990s and the last decade. That is the Sloan Digital Sky Survey and the Hubble Space Telescope.
WFIRST is a NASA observatory that has the top ranking of the National Academy of Sciences to launch in the 2020s. It has the same image precision and power as the Hubble Space Telescope, but with 100 times the area of sky that it views.
Looking at a large fraction of the sky allows you to get a more complete accounting. For example, the stars in the Large Magellanic Cloud, which is the nearest galaxy to us, or the stars in the galactic bulge. So you can do a much more complete accounting in a much shorter amount of time. The particular thing I'm interested in using WFIRST for is to actually do a statistical census of planetary systems in our galaxy. And what we're looking for is gravitational microlensing events. These are cases when another star passes in front of our line of sight to a background star, and it makes that background star get a little bit brighter due to the gravity of that foreground star. And that allows us to find planets.
What WFIRST will do is it will have what we call a coronagraph. A coronagraph lets us image and characterize really dim planets next to very bright stars.
No matter how good a telescope that you build,
it's always going to have some residual errors. It's going to be the first time that we're going to fly an instrument that contains these high-format deformable mirrors that are going to let us correct for errors in the telescope. That's never been done in space before.
WMIL first will allow us to potentially make groundbreaking discoveries, finding out what dark energy is. So this will tell us if dark energy is an unknown form of energy or if it's a modification of general relativity.
Single WFIRST images will contain over 1 million galaxies, and we can't categorize and catalog those galaxies ourselves. Citizen science allows interested people in the general public to solve scientific problems. And so one of the things that I'm really excited about is enabling this bridge where the general public can get involved in doing actual science.
For me, it's a really exciting opportunity to play a significant role in a mission that I think will be one of the most powerful telescopes that we have in the 2020s, and will be some of the most important things our country does in space in that time frame.
With these new eyes in the sky, there seems no limit to our ability to unlock the mysteries of our universe. NASA's latest robotic lander, InSight, descends to the surface of Mars. A challenging effort greeted with elation.
Touchdown confirmed.
Meanwhile, an orbiting ESA satellite, ExoMars, begins its own exploration of this enthralling planet. The majestic stereo imagery of Mars as seen from orbit reveals a planet of dynamic texture and form, slowly revealing its secrets.
We've sent a lot of missions to Mars in the past. We've sent rovers, we've sent orbiters, they've done a lot of really great science and a lot of really interesting measurements, but those measurements just scratch the surface of Mars. We know a lot about the surface of Mars, we know a lot about its atmosphere, and even about its ionosphere, but we don't know very much about what goes on a mile below the surface, much less 2,000 miles below the surface down to the center. And this will be the first mission that's going to Mars specifically to investigate the huge extent of Mars below the surface. The basic idea of InSight is to map out the deep structure of Mars for the very first time. We're going to map out the thickness of the crust, the size of the core, the composition of the mantle and core of the planet, sort of get the first map of the deep inside of Mars. It's going to Mars to do the science, to make the measurements that scientifically and personally I've been waiting for over 30 years for. As a graduate student, I was doing research on Mars, and I just needed to have the thickness of the crust. I just needed the thickness of the crust, and we didn't have it. And seismology was the way to do it. And so I thought, well, maybe someday somebody will put a seismometer on Mars and get this measurement so I can do my research. And so it's kind of an amazing journey for me to look back and say, I'm the guy who's actually going to put that seismometer on Mars, get that information, and now I can go back and finish the job I was trying to do 30 years ago. It's an amazing feeling.
The InSight mission will finally provide seismic information of Mars that scientists have been wanting for since the very first Mars lander, Viking. It had a seismometer on it, but for a variety of reasons it never got back any seismic data. There's been many other attempts to get seismometers onto the surface of Mars for very good science reasons, but they've, for one reason or another, never been successful. So now we're right on the very edge of getting a seismometer onto Mars that will finally give us back seismic data. That seismic data is incredibly important to scientists because it gives them an idea of what the size of the crust, the mantle, and the core are, as well as the properties of each of those, which are the basic internals of every rocky planet.
The most fun or interesting thing about InSight from an engineer's point of view is really that we're playing the claw game super far away on Mars. We're taking this grapple and we're going to pick up an instrument and lift it up off the deck and put it down on Mars. So I like to say that we're playing the claw game on Mars with no joystick.
Next, a wind and thermal shield will be lowered over the seismic instrument to protect it from the environment. The second instrument, the heat flow probe, will be placed on the ground and over time will hammer itself down to take subsurface readings.
There's a lot of international partners on InSight. It really takes a whole world to produce an exciting mission like this. So most of our science missions are actually being supported by our international partners. So for example, the SEIS instrument, our seismometer, has support from the French, the Germans, the Swiss, the UK folks. So we have a variety of those people. The heat flow and physical properties probe is being provided by the Germans with some support from Poland.
InSight is a mission to Mars, but it's much, much more than a Mars mission. In some sense, it's like a time machine. It's measuring the structure of Mars that was put in place 4.5 billion years ago, so we can go back and understand the processes that formed Mars just shortly after it was accreted from the solar nebula. By studying Mars, we'll be able to learn more about Earth, Venus, Mercury, even the Moon, even exoplanets around other stars.
ESA's Trace Gas Orbiter mission arrived at Mars some time ago. Since then, this 3.5-ton spacecraft has been gently brushing the atmosphere to gradually adjust its orbit. In ESA's Planetary Missions Control Room in Darmstadt, Germany, flight controllers have been checking systems and commissioning instruments on the ExoMars Trace Gas Orbiter. Now it's ready to begin its science mission.
It has been a long time since we arrived at Mars in October 2016, and we have had a very long period, 1 year, of aerobraking, which consisted in reducing the orbital period from the time when we arrived, where it was actually several days, to 2 hours, which is the nominal period for science observations. I'm looking forward to the next few months enormously because the TGO will finally be able to show its full capability, the full capability of its instruments in terms of accuracy and the quantity and quality of data, pictures, spectra. And also because we will be able to do joint observations with our previous spacecraft at Mars, Mars Express, which is still alive and working after 15 years, actually. And for ESA having two spacecraft around Mars in complementary orbits from a scientific point of view is very exciting and will allow certainly some very interesting discoveries and observations.
ExoMars will fill a double role when its partner rover is dispatched to Mars in the coming months in the search for life on the dusty planet.
It is a communication satellite on top of being a science orbiter. The so-called relay function allows us to communicate with all landers and rovers on the surface of Mars. At the moment, there are only rovers and landers from NASA, Curiosity and Opportunity. Some tests had been done already soon after arrival at Mars. And now we are going to start a campaign to calibrate and determine the best performance to relay data.
The Trace Gas Orbiter's primary mission, however, is to identify gases in the Martian atmosphere, particularly methane. First hinted at by Mars Express, and then by NASA's Curiosity rover as it sniffed the atmosphere with special sensors.
Well, we know that the lifetime of methane is very short, just a few hundred years. It will be broken down by the sunlight, by the UV ultraviolet component of the sunlight. So if it is there now, we know that it has to be refilled all the time. And where does it come from? That's the big question. It cannot be synthesized really in the atmosphere. It has to come from the surface or from the subsurface. But what are the processes that produces it? This is what we want to find out. One possibility is that it is some geological reaction between minerals and water. Another possibility is that actually also are microbes down buried underneath the surface that is producing it today or has produced it a long time ago and they're all dead now, but that the methane has been kept underground and with some mechanism is released to get up into the atmosphere. So these are all these kind of things we try to find out.
By using the orbiter's powerful spectrometer, scientists hope to discover whether the methane comes from a geological or biological source. 95% of methane on our own planet comes from living organisms. The ExoMars rover, landing in 2021, will drill up to 2 meters beneath the surface to search for this evidence of life. And the rover, as well as NASA rovers and landers, will use the orbiter to keep in touch with Earth. Mars exploration is an international endeavor, and every mission adds to our understanding of this alien world, a place that some of us might someday call home.
Planetary exploration is always very exciting, but Mars, of course, has this very special thing, is that there is actually a place that you can imagine yourself walking on. You eventually, within not too far in the time in the future, surely people will be walking on Mars. And that makes it very exciting. And then to think about this idea that there might have been some kind of life, or even exist today underground on Mars, that makes it a very special place.
Curiosity landed in Gale Crater on an ancient lake bed. A few months after arrival, It drilled into sedimentary rocks and detected traces of organic molecules using an instrument called SAM.
Well, the SAM instrument detected a variety of organic molecules in a sediment that is from an ancient lake bed in the middle of Gale Crater. And what's important about these is that we now have a lot more certainty that there's organic molecules preserved at the surface of Mars. We didn't know that before. But what's interesting is that we don't know what the source of these organic molecules is right now. There's just not enough information from that. However, if we drill deeper and we look around a little bit more, we might actually be able to get to that information and tell, did they come from life? Did they come from geological processes? Or maybe they were from meteorites that were deposited in the lake. We just don't know right now, but hopefully we'll figure that out.
Curiosity is searching for carbon-based organics.
SAM made the new detections by heating samples of crushed rock to very high temperatures, above 1,000 degrees Fahrenheit. This vaporized the samples and released several species of small hydrocarbons like benzene and propane. Because the hydrocarbons were released at such high temperatures, they may be the fragments of bigger, heavier molecules within the rock similar to kerogens. On Earth, kerogens are found in rocks like black shale and coal and are the products of ancient plant and bacteria.
Some other organics have been detected, like thiophene, which contains sulfur. Introduced by geological processes, this sulfur acts as a preservative, binding organic molecules together and making them resistant to oxidation, so preserving them for millennia.
Organic molecules could be the food for life, or they could be the product of life, or maybe they're from something altogether different, such as geology or meteorites that were deposited into the lake. We don't know what the source is, but there's a story there, and we're going to uncover what that is.
Scientists still don't know if the discovered organics on Mars are biological in origin, but it's exciting to find such old material preserved right at the surface. This finding is also encouraging for future exploration. So for a time, Curiosity continued to travel, find interesting outcrops, drill holes, take samples. Then, inexplicably, something went wrong.
The drill's feed mechanism, which is responsible for moving Curiosity's drill bit into and out of rocks, didn't move when commanded. When Curiosity drills into a rock the way it was designed to, the drill's two stabilizer posts touch the rock first to steady the arm while the drill's feed mechanism moves the bit forward into the rock. Without the feed mechanism working, we can't drill that way. To solve this problem, we do what we always do. We worked it out in the test bed using Curiosity's twin on Earth. Our team of engineers and scientists have been working for months to figure out a way to collect and deliver rock samples without using the feed mechanism. Here's what we came up with. Using our new technique called feed-extended drilling, the stabilizers are not used. The bit is now in a forward position extended past the stabilizers. Moving the drill straight into a rock and retracting safely without the stabilizers is challenging. We move the arm instead of the feed mechanism to place the bit onto the rock and press it forward as it drills. After making contact, we apply a light preload and drill a shallow pilot hole. We use a force sensor in the robotic arm to give Curiosity a sense of touch. This lets Curiosity adjust its arm motion and avoid getting stuck while drilling, kind of like you might adjust your arm while drilling into a wall at home. After drilling, we use a similar technique to retract from the hole without getting stuck.
With Rover 2020 design and construction well underway, engineers will be sure to avoid such a problem with Curiosity's cousin, which will land in the Jezero crater in 2020. 2020 will be a banner year for the exploration of Mars. In addition to the launch of NASA's Mars 2020 rover, the European Space Agency and Roscosmos are sending the ExoMars rover to the Red Planet. Rover 2020 and its companion helicopter will no doubt expand our search for life, past or present. However, the big advance forward in organic analysis will be the game changer. Both rovers will carry on board a MoMA.
The Mars Organic Molecule Analyzer, or MoMA, is the largest and most complex instrument on the rover. Its mass spectrometer subsystem and its main electronics were built and tested at NASA's Goddard Space Flight Center, which also contributed mass spectrometers to NASA's Curiosity rover and MAVEN orbiter. MoMA is designed with a mix of proven hardware and innovative new technologies. Here's how it works. In gas chromatograph mode, crushed Martian rock is put into an oven and heated to 900 degrees Celsius in just 2 minutes, vaporizing the sample. Molecules of hot gas rise up and flow into a narrow 20-meter-long tube. Special coatings inside the tube cause molecules with certain chemistries to slow down more than others, separating the mixture of molecules over time. Next, a beam of electrons ionizes the molecules, giving them a positive electric charge and deflecting them towards the linear ion trap. The ions are caught by a fluctuating electric field and sent to a detector to determine the chemical makeup. While gas chromatography has been used to study Mars since the Viking program, MoMA has a second method for preparing samples that has never been used on another planet. In laser desorption mode, a sample is placed beneath a powerful ultraviolet laser. A beam of energetic light builds within the laser and fires in a billionth of a second, concentrating its energy onto a spot smaller than a grain of sand. This rapidly vaporizes a portion of the sample, releasing large organic molecules that could be broken down by oven heating. The laser shot also ionizes some of the molecules, allowing the vapor to head directly to the linear ion trap. Neutral molecules are ejected by a vacuum, while the remaining ions are sent to the detector to determine their chemical makeup. Laser desorption will enable MoMA to detect long molecules like lipids, the building blocks of cell membranes, a leap forward in the search for life on Mars.
The question of life on Mars is among the most important in planetary science, and the evidence may be buried just below the surface. With the help of MoMA, we will take one step closer to uncovering the answer. These images will pave the way to a new understanding of life in our solar system. CubeSats. They've been around for a while now. the domain of universities and institutions wanting to teach and gain experience in space. They're low cost, light, and very adaptable. Not only that, but they're also easy to send into orbit. Now, business is eyeing off these microsatellites with big plans for the future. The traditional satellite is an industrial and technological marvel. Designed and built from the ground up for a specific purpose with a long life expectancy, some communications and global positioning satellites are built on an off-the-shelf platform design to help alleviate costs. Launching them into orbit, however, is no easy feat. Weighing as much as 50 tons, they have to be placed in a geosynchronous or high polar orbit, which requires expensive launch facilities. The CubeSat satellite, or microsatellite, devised as a training and development tool for university students, has now taken on a life of its own as a low-cost alternative to the conventional satellites in particular roles and for new purposes not previously considered.
A CubeSat is a nanosatellite basically in a box size. The standard dimensions of a CubeSat would be 10 by 10 by 10 centimeters, and you can have multiples of that unit. So you could have a 3-unit CubeSat, for instance, 10 by 10 by 30 centimeters, and all of the satellite equipment has to fit inside that box. The origin of CubeSats goes back over 10 years. In the US, university professors were looking for ways to allow their students to essentially build and fly satellite hardware during their degree courses. And so that was envisaged as a very low-cost way for universities to get their students well educated in the engineering skill.
University student teams from around Europe have been busy in the last months making the final preparations for ASIO, the European Student Earth Orbiter. ASIO is preparing the space workforce of tomorrow. The student teams designed, constructed and tested the essential parts for the mission.
During its whole project life cycle, ASIO engaged several hundred students, and already before launch we can say that it achieved all its main educational objectives.
Launched aboard a SpaceX small satellite-dedicated Falcon 9, ASIO was released into a polar orbit. Aboard the satellite there is a radio amateur communication system by the University of Surrey and AMSAT UK in the United Kingdom. This enables ASIO to transmit real-time data to schools and universities for science and engineering lessons.
I participated in the LMP project. It is a bit a personal project for me because there is a component which I have in the design, and I wrote my thesis from this component.
I've been involved in the development and testing phases of the power distribution unit of the ASIO satellites. It's an amazing feeling that your device will go up into space and it's ready, it's working well, and I'm so happy.
ASIO is a complex system, and in the end I think it was challenging activity for all the payload teams. We had the chance to stay with them. We had the chance to teach them a few things that typically are not so common in academia.
ASIO gave us the competence to actually build any scientific instruments here in the observatory. It gave us both the competence and also the connections with ESA, and we learned a lot from the projects in order to develop our further missions.
there's been some evidence that lightning produces gamma rays, and this is really the first satellite that's going to go out and investigate if and how and where and everything associated with gamma rays coming from lightning. There's been evidence, and others have seen this, but again, there's never been a satellite dedicated looking down at Earth for these terrestrial gamma ray bursts.
We want to make artificial signals similar to lightning and see what the board does, make sure it's filtering those signals the way we want.
We're going to put it into HDL code and then get it through this chip.
One of the tenets of the CubeSat program is to involve undergraduate students at all levels, from design to building to some of the theory, data acquisition, every aspect of this. So we're really training here the next generation of space scientists, of satellite engineers. As soon as the launch goes up and they know they're a part of that satellite and data's coming in, I mean, that'll be with them throughout their life.
Where else could CubeSats be applied? A major space mission to Mars, InSight, was a perfect opportunity to test out some new technology.
Liftoff of the United Launch Alliance Atlas V rocket.
The Atlas V RD-180 main engine ignites and generates more than 860,000 pounds of thrust.
Flying with the InSight spacecraft to Mars were two CubeSats. Called Mars Cube 1 or MARCO, they were a technology demonstrator and the first use of miniature modular CubeSat spacecraft design in deep space. The pair of briefcase-sized spacecraft, MARCO A and B, were launched on the same rocket as InSight and traveled independently of the main craft. They carried a number of communication and navigation flight experiments. Although NASA emphasized the experimental nature of the CubeSats before the InSight landing, the MARCO spacecraft performed as intended, receiving the UHF telemetry from InSight during its entry, descent, and landing phase, and rebroadcasting it at X-band frequencies received by NASA's Deep Space Network. This vindicated CubeSats as another tool in the exploration of deep space. To top it off, MARCO B managed to take a photo of Mars and transmit it back to Earth as it passed by the planet. The rush to exploit CubeSats is on. Scientists and engineers have begun designing, building, and launching various designs for specific missions and for testing new technologies in space. Rocket launching companies have been quick to respond, developing and flying dedicated launches for the emerging small satellites market. SpaceX and ESA's Vega launchers are among these companies, while the Electron from Rocket Labs has already begun flying commercial CubeSat launches and is planning a monthly service.
My involvement goes back 10 years from when I was working in the education office at ESA. So indeed, I was responsible for managing university CubeSat projects that we would then later fly on the maiden flight of the Vega launch. We had 7 CubeSats that flew on the Vega maiden flight, and actually many students were involved in those projects, and they went on to graduate, and many of them formed their own spin-off companies, which now forms the basis of the CubeSat industry today. What we're seeing is that the same technologies that are being exploited terrestrially for aerial drones are also being exploited by CubeSats. So I like to think that that same technology will enable CubeSats to become the autonomous drones of the space domain. With the capability of CubeSats to become autonomous space drones, they will have the performance to be able to perform autonomous navigation, close proximity operations around other target objects, and also be able to fly in swarm formations. So these are very advanced architectures. We might also see them being able to perform autonomous rendezvous and docking together, forming building blocks to build up larger structures in space in the future. When we do the CubeSat projects, of course, the standard engineering approach combined with the access to ESA facilities and technical know-how gives an added value to ESA member states to ensure that we maximize the probability of mission success within the tight financial constraints of each project. So far, we've flown one technology CubeSat in orbit, GOMX-3. That mission has been very successful. It's recently re-entered the atmosphere, so the mission has been completed successfully. Now we are preparing to fly another CubeSat called Carmen. It's designed to demonstrate re-entry technologies, a very exciting and challenging project. And beyond that, we have another 4 technology CubeSats in development, and we're already talking to our member states about starting many new projects in the future for these technology demonstrations.
The use of microsatellites for commercial and industrial purposes is a growing field of interest, as is the concept of the Internet of Things. One company has combined the two into what may become the next great technological revolution. Alongside household names like Microsoft, Google, and SpaceX, you may soon be adding fleet to the list.
So Internet of Things is a concept that probably started 5 to 10 years ago. You know, people were talking about this. There are 25 billion devices coming online in the net. It's the fourth industrial revolution. Everything will be connected. It's going to change our lives. I kind of separate the concept in two. The smart cities, so when our life will change into buildings, you know, your Fitbit connected to your fridge and your car driving itself, and the smart fridges, smart traffic lights, and so forth. And also smart industry. So what happened in remote areas, in a big farm or in a big oil and gas company, a big mining, that's a heavy industrial revolution. So Internet of Things is the idea that we are kind of changing the way we operate. We have spent 40 years connecting people and, you know, bringing computer inside factories, and suddenly everyone has got a computer that cannot live without it. You know, if there's a day you cannot use a computer, you go home because what am I supposed to do? So in the next 40 years, things will change the industry in the same way the computer did. So imagine a big farm, suddenly everything will be connected, you know, from the soil to the literally soil, you know, content to animal tracking, weather station, thousands of sensors that we allow the farmer to literally understand so much of the way they operate that we will solve the biggest problem on earth, you know, water leakages and drought and so forth. But that goes into, you know, transport and logistics, not measuring pallets and fruits traveling all over the world. I think we waste 60% of our food in supply chain. So there are big changes happening, and this is all about little sensors being connected. The problem is that this big industry that I'm mentioning, they have no 3G. I mean, 3G, 4G, even 5G covers the population, but 95% of the world is unconnected. And this is where our farms are, where our mining and oil and gas companies are, where the shipping containers are. So it's a kind of a problem that terrestrial infrastructure cannot solve. And well, we got space, or we solve it from space.
The potential for a constellation or swarms of CubeSats to become powerful research and communication tools is now starting to be explored. The ability to track almost anything across the planet is now a reality. The possibilities seem almost endless.
Internet of Things is interesting because with one satellite in LEO, so low Earth orbit, you cover almost every side of the planet. And customers see you once a day. It's not much. You know, it's not really good for high-speed internet or talking Skype or checking YouTube, but it's great, you know, for a valve, or a soil moisture sensor, or a cow. You don't want to know where a cow is every single minute of your day. Probably you do, but once a day is perfect for LEO. But when you reach 100, or for us it's 100, it probably will be even less, the latency is so good that you can actually take all some, you know, high pressure emergency applications, like safety and security, in which you want to send the data and grab it straight away and send it to the customer straight away. But the good things of Internet of Things is that you launch one satellite and then you're in operation. You can serve everything now. So we had launched 4 satellites last year. It was a great journey of fleet. You know, for a startup, we launched them in 24 days. 2 with Rocket Lab was first Rocket Lab launch of nano satellites was commercial. So it was literally like, what is going to happen here? And then of course SpaceX and PSLV. But the first satellites we built was almost 1 year. The second one 2 months. When we launched with Rocket Lab, by the time we start building the satellites, to the time we booked the flights and the time we were in space, was 4 weeks. You know, so There's a big revolution also on the launcher side, that can put us in space quite fast.
This startup company seems to have hit the nail on the head. Low-cost terrestrial sensors can be hooked up to almost anything, and their status uploaded to the CubeSats for transmission to the clients via the net.
The people that are booking these sensors, they come from the biggest oil and gas company in the world with all the farms in South America. This is big customer. So we are entering a phase in which, as most startups are starting so little, is having massive customer impact. That satellite company that operates for $1 billion in many, many years don't have. So it's time to see at these satellites and understand it's not a game anymore. This is going to be $1 billion companies very, very fast. So it's quite exciting.
This system could increase efficiencies and save waste across the globe.
Earth needs help. Earth needs monitoring, Earth needs efficiency, Earth needs water to be saved, and food to be not wasted, and people to be safe. So millions of cents is going to change the world forever. It's going to be billions. When we started Fleet, we started with a dream of connecting the entire world and millions of devices. We call it 1F. It's our first constellation, and for us 2F is going to be the Moon, and 3F is going to be Mars.
The potential for space exploration is exciting. Quick and efficient data networks dispatched to the Moon, Mars, and beyond, or even swarms of CubeSats surrounding an asteroid or a spacecraft during rendezvous, sending back data and video. The scope is limitless.
Imagine you can have a constellation to track every robot and things just to make sure where they are, and this is just the beginning. And the reality is that when the big entrepreneur will go to Mars, they will put so many things, and you want to make sure they're tracked, and it's a complicated exercise. And a CubeSat, it's a way to go there fast. When you need to move a big satellite to Mars, it takes a long time. And you launch a storm of bees, eventually they will get there. But eventually we'll go there, and we will have to do the same. We will have to have big responsibility when we start conquering the other planets, monitoring what happened. I think, it's going to be fleet responsibility as well, I guess.
The American relativist John Archibald Wheeler succinctly explained Einstein's equations on relativity this way. Space-time tells matter how to move. Matter tells space-time how to curve. For theoretical scientists to move forward, Einstein's equations now need to be either proved or disproved. Two fundamental rules of the universe, as theorized by Einstein, are that light in any form moves at the same speed, meaning that space-time is smooth, and secondly, that the laws of physics are the same everywhere in the universe at any time. Since the more recent discovery that the universe is expanding at an accelerating rate, other theories counter to Einstein's have been put forward. One suggests that space-time is lumpy, and that higher energy light will feel it more as a hindrance. To put this theory to the test, scientists needed to compare the speed of two particles of high energy light.
So you might be thinking, two tiny particles of light, why is that important? Well, you need to take the very large and the very small together to understand the universe as a whole. So far, Einstein's theory of relativity, which describes space and time as a smooth fabric that's distorted or bent by massive objects, has been a spectacularly successful explanation of gravity and the large-scale behavior of the universe. Whereas quantum mechanics, another spectacularly successful model, describes the workings of atoms, subatomic particles, and some of the fundamental forces of nature. But scientists have never been able to reconcile the two. Both relativity and quantum mechanics are equally fundamental in their own regimes. So scientists want to find a theory of everything that describes the universe as a whole.
Several ideas which attempt to reconcile relativity and quantum mechanics suggest that space and time are not actually smooth and uniform, but are instead a seething froth when seen at the smallest scale, like bubble wrap. A low-energy, long-wavelength photon is unaffected by the lumpiness of space. But a high-energy, short-wavelength photon is hindered by the froth. This makes it move more slowly than lower-energy radiation, so it breaks Einstein's law that all light particles must travel at the same speed. To test this theory, they needed Fermi, the orbiting gamma-ray detector.
We observed a gamma-ray burst. A gamma-ray burst is a huge explosion. That gamma-ray burst produced a large number of photons, one of which had enormous energy, very short wavelengths. Those photons traveled 7 billion years to reach us, and yet the highest energy, the shortest wavelength photon, arrived within 900 milliseconds of the lower energy photons. That's a little bit like racing two speedboats, one through water and the other through molasses, and having them arrive at the same time. It just doesn't happen. Because Fermi saw no delay in the arrival time of the two photons, it confirms that space and time is smooth and continuous, as Einstein had predicted. And it shuts the door on several theories of everything that had predicted that space and time might be foamy enough to interfere with light. And the observations that we've made of these two photons with Fermi takes us one step closer to achieving the goal of having a theory of everything that combines the most successful aspects of quantum mechanics and relativity into one unified theory.
Einstein's theory also predicted that gravity could bend light, an astronomical effect as seen here called an Einstein ring. Gravitational lensing is where the light of a galaxy behind another gravitational body is bent around it, forming a ring of distorted light. But do the numbers add up? And can the mass of the interfering object be measured using this theory?
So we've known for a long time that on the scale of the solar system, general relativity is either the correct theory of gravity or extremely close to correct. But we don't actually know whether general relativity is the correct description of how gravity works on the scales of individual galaxies or of the universe as a whole. So we used two phenomena. One is called gravitational lensing. So general relativity says that when you have a massive object like a galaxy, that causes space-time to be deformed. And that warping of space-time means that if you have a second galaxy behind it, the light coming from that second galaxy will be deflected. And if the deforming of space-time is enough, you can get multiple images of that background galaxy warped into what we call an Einstein ring. And the radius of that ring, how big that ring is, tells you how much warping of space-time is going on. So we used two telescopes to do this. We took an image of the gravitational lensing using the Hubble Space Telescope, and that let us measure how big the Einstein ring is. And then we used the very large telescope operated by the European Southern Observatory in Chile to measure how fast the stars are moving in the lensing galaxy. So we took spectra. This is measuring how much energy is emitted basically in each color. And those spectra tell us how fast the stars are moving in the galaxy. Measuring how fast the stars are moving tells us how much gravity there must be holding those stars in their orbits. And so comparing the amount of mass that we infer from that with the amount of warping of space-time that we see from the lensing, we're able to test whether the amount of warping is consistent with general relativity.
In 1917, Einstein created the concept of a cosmological constant in his calculations to balance out gravity in his theory of general relativity. He later abandoned this concept, considering it erroneous. However, with the recent discovery of an accelerating universe, that constant might help explain dark energy.
Dark energy is a hypothetical substance that explains why the expansion of the universe is accelerating. So the universe has been expanding ever since the Big Bang, but what's odd, and we've only known this for the last 15 years or so, is that acceleration is getting faster. It's accelerating. Now, naively, you would expect that all of the gravity in the universe, all of the mass, would cause things to pull together and slow down the expansion or have it carry on going at the same rate. You can't really come up easily with a way of explaining why the expansion is getting faster and accelerating. Now, one way of explaining dark energy, one way of getting rid of dark energy entirely, is to say, well, all of that interpretation is based on assuming general relativity is the correct theory of gravity. Now, if it's not, and a lot of theoretical cosmologists have worked on this in the past, you can come up with ways of accelerating the expansion without introducing a dark energy. Now, our work, which we found that general relativity is the correct theory on the scale of individual galaxies, tells us that if you want to explain away dark energy, you have to maintain the validity of general relativity on astronomical length scale.
Another factor of Einstein's relativity is that gravity and space-time will function in a predictable manner everywhere.
The whole theories about the formation of the universe, how the universe is evolving, are based on one philosophical and fundamental assumption, which is that the laws of physics are valid everywhere in the universe and at any time in the universe. While here on Earth, we can only prove those laws of physics now and on certain circumstances. So it's very important in astronomy to also check that those laws of physics are still valid, where the gravitational fields are much stronger.
Recently, it has become possible to put that theory to the ultimate test. The effects of Einstein's general relativity will be assessed in the most extreme gravitational conditions imaginable, at the heart of our own galaxy.
We think we know that this object we have in the galactic center is a black hole, but to prove that, without any doubt, we have to come so close that we actually have to measure the fabric of space-time and see that it's that which the theory of Einstein predicts. So that's the concepts. Then comes the question of difficulty, and I have to say, ooh, that was a long path. It was very, very difficult because while gravity is sort of an obvious thing, you stand here on Earth and you sort of have an idea what it is. In reality, it's an extremely weak force, and the effects of general relativity are extremely small. So you have to measure to a precision which we are normally not used to in astronomy. Well, you see, the center of Milky Way, where we suspect there is a black hole, has stars orbiting this central black hole. And these stars are our measurement objects, if you like. They test the gravity of the object. And there's one star in particular, which we've been following now, believe it or not, for 25 years. That's more than half of my scientific career, with telescopes here at ESO in particular. And we've charted the orbit of this star, and we know that around this time, this star will make it as close as 4 times the distance of Neptune to the Sun. That's 17 light hours. So that's very, very close. And that's the unique opportunity to, in fact, test out the gravitational theory, because there gravity is the strongest. The star now moves with about 3% the speed of light, or several hundred times the speed of the Earth around the Sun. And that's when these tiny little warps in space-time, which cause general relativity to be different from Newtonian theory, to be most pronounced. So it took us about a decade between 1990 and 2000 to basically come up with robust evidence for this mass. And then in 2002, nature gave us just an absolutely miraculous star which moved so close to this object that you could see it zip around the mass in a matter of only a few years, and that gave us absolutely fantastic information. We could estimate the orbital parameters, the mass, etc., and we were fairly sure it's a massive black hole. Now the orbital period of this star is 16 years, and these measurements we took here on the then new Very Large Telescope we took in 2002. Take 16 plus 2002, and that's 2018. So our star is coming back to its original, very close position near the black hole. That's the time when we want to be there and make these measurements.
Preparations for this breakthrough observation began in early 2018 at ESO's Paranal Observatory. Their cutting-edge astronomical equipment was readied to make measurements of one of the most extreme gravitational laboratories at the center of the Milky Way.
For the discovery, a combination of 3 instruments of ESO were used: NACO, Symphony and Gravity, and all of those instruments are unique in the world. NACO is adaptive optics in the infrared. We don't have so many in other telescopes. Symphony is a high-resolution spectrograph, very important to measure at which speed the star is coming to us or going from us. And Gravity is an interferometric instrument, the only one in the world that can combine 4 big telescopes, 8 meters telescope, with a baseline of 130 meters, so having the same resolution as a 130-meter telescope. And it has, in addition, the capability to do astrometry, very accurate astrometry, so it measures movement that are the equivalent of an astronaut on the moon moving a flashlight by about 10 centimeters. And the combination of all these instruments, interferometric and classical spectroscopy, adaptive optics, is what makes ESO unique. It's having all of them on the same side in a position where you can observe the galactic center in good conditions.
So by testing, by measuring these predicted physical teeny effects, they are a very, very small fraction of what we knew so far. That's why we have to make such precise measurements. That's how we can test general relativity in this domain.
We need to get very sharp images. And the best way we can get sharp images is to make big telescopes. But since we don't have these very big telescopes, we combine telescopes. We create a super telescope, in this case, which is 130 meter diameter.
Even with the impressive size of the Very Large Telescope, the only way to precisely measure the path of the star around the supermassive black hole took some innovative telescope teamwork.
For our work so far, what we've done is we've taken pictures with the single big telescopes, the single 8-meter telescopes, and make them as sharp as you can be. The problem is, and you see this in my hair, there's wind. And the wind distorts the waves. And so either you go out in space, very difficult for an 8-meter telescope, or you take the 8-meter telescope and you repair the distortions, which the Earth's atmosphere does. Like on a hot day when you travel along a road and you see the flimmering of the distant approaching cars. So that's what we do. That's called adaptive optics. And that makes the images with single telescopes already very sharp. But that's not sharp enough for what we want to do now. We really need to make still better, still 10, 20 times sharper images to see the tiny effects of general relativity. And that we do by taking into account that ESO not only has 1 telescope, but 4 of these gigantic 8-meter telescopes, and we can bring them together as if it's one. That's a very challenging experiment, but we've done this now, and so we are ready to make these measurements at an unprecedented precision.
So we combine the light from 4 telescopes, the very large telescopes, here in the center of the mountain of the observatory. The 4 telescopes are separated by 130 meters, which means that our super telescope can make 20 times sharper images than a single telescope.
We have all 4 telescopes working together, and in addition to these 4 telescopes we have a beam combiner, and this combines the light from all the 4 telescopes, and this is gravity. Gravity is, of course, it's the best, because we can really trace the orbit of this star very, very carefully with really good accuracy, so we can now get very nice orbits, and we're trying to test all our theories with this very nice data we have now.
2 other state-of-the-art instruments will reveal an effect called gravitational redshift. This is visible when light from the star is stretched to longer wavelengths by the very strong black hole.
We actually expect that we can see general relativity, and how can we see that? It's actually a slight deviation of how the star is moving, and this deviation we can see in the first place with the so-called Doppler effect. It's currently approaching us, and it will fly away, and this Doppler effect is actually something we can observe by the means of spectroscopy, and spectroscopy in turn means that you need a spectrograph, and such a spectrograph is Symphony, and that is the instrument which will be the one which actually is observing the relativistic effects.
Now, after an epic 26-year observing campaign, the effects of Einstein's general relativity have been clearly seen for the first time.
So the experiment we're doing is extremely simple in some sense. We are just measuring the motion of stars around the black hole. That is very much like Earth goes around the sun, and you can actually calculate the mass of the sun from the knowledge that Earth takes a year to go around the sun, and essentially we try to do the same. We try to measure the mass of the black hole by seeing how the stars fly around it.
And right now we are observing this passage as the star moves into this critical curve around the black hole.
For scientists, a spectacular show of orbital mechanics and relativity.
So what were the most exciting moments in the observing campaign? I think actually it was in the very beginning, about 2 years ago, when we for the first time pointed to the black hole and to the star, and actually we've seen that both of them, and this was a big surprise for us, because we did not expect it. Actually, it's right at the field of view of what we have, and so this was very revealing to actually see it, that we can go to very faint, that we see the faint black hole all the time and the star nearby. And the other most exciting probably was that this year, when the star was moving so fast at a fraction of the speed of light, that you could see it from night to night. This was very exciting to see.
And the combination of all these instruments, interferometric and classical spectroscopy, adaptive optics, is what makes ESO unique. It's having all of them on the same side in a position where you can observe the galactic center in good conditions.
The beauty of it is that it's a very simple experiment in the phenomenon. Yeah, there are some technical challenges that you have to overcome to build the instrument and perform the experiment, but the concept is very simple. You can probe the black hole properties, and then you can probe the gravitational field, which is a very strong one, and up to now, when whatever tests for the general relativity or this geometrical theory of gravity that we have has been in the solar system, and also some pulsars, but in this very strong regime, it has not been tested. So this is just a starting point for it, with the developments like instrument developments and the new telescopes. We will do more and more of this.
More than a century after he published the paper setting out the equations of general relativity, Einstein has been proven right once more with the combined resources of the ESO.
This is one of the huge benefits of ESO, and the way ESO works is that there is always a very strong collaboration between ESO and its institutes in its member states. which is very unique in the world because it enables ESO and the ESO members to undertake projects like gravity, which are so complicated that you need a strong team.
Well, what comes next? For the next years, we have a pretty good outlook of what will happen. So the next effect, which we will see, is a Schwarzschild precession. This means the orbit of the star will rotate. The ellipse will rotate a little bit. And so this is an effect which we will see next year. Pretty sure about it. Then we come to more subtle effects of general relativity, but even more exciting. This is about the space-time itself around a black hole. So the space-time around a black hole will rotate with the black hole, and so this will move the orbits of the stars yet in another direction. And this is very exciting because this property is very unique to general relativity, and we will only be able in that black hole in the center of the Milky Way, we will have the precision to measure that.
With the theory of relativity dusted off and placed back on its pedestal, what remains is for scientists to work out what dark energy is and how it affects the known universe. We are finding more and more exoplanets, more and more locations for liquid water, and the possibility for life as we know it. But where are the alien civilizations? Where are the technologically advanced creatures? Why can't we find signs of other sentient beings? Where are their signals out there amongst the stars? Perhaps the answer to that age-old question, are we alone in the galaxy, is a yes. American astronomer and astrophysicist Frank Drake established the search for extraterrestrial intelligence, or SETI, back in 1960. Listening to the stars and the noisy galaxy, trying to find signals that are deliberate, messages from other planets where life has evolved an intelligence, a technological civilization like our own, able to comprehend the vastness of space. Like us, looking for the answer to that age-old question, are we alone? There are 3,700 known exoplanets so far. NASA's TESS is going to find lots more. The European Cheops mission will specifically study the known exoplanets and look for more around our brighter stellar neighbors. Multiple planetary systems and terrestrial, Earth-like planets are coming up trumps, and we've only been looking for 15 years. We have been looking and listening for nearly 60 years now with zero results. No radio signals, no laser or other light flashes in our direction, no attempts at communication that we can detect. So where are all the aliens? Well, it's a complicated question. stars that can harbor Earth-like planets, viable exoplanets that can sustain liquid water. As for life, how long does it take to generate life? Then, how long to evolve into intelligent life? Will that intelligent life become technological? How long will an advanced civilization survive? Tough questions when you only have Earth as your example. Then there is the time factor. The universe is 13.8 billion years old. Our star, the Sun, is 4.6 billion years old, and probably a third or fourth generation star. Earth is 4.543 billion years old. Our moon is just the right size to stabilize Earth's rotation and provide ocean tides and sea currents. Life on Earth is at least 3.5 billion years old. Several major climatic and asteroid interventions steered the evolutionary cart leading to us, Homo sapiens, 200,000 years. Our civilization began around 6,000 years. The industrial age is just over 200 years. The ability to send signals into space, maybe 100 years. Powerful radio signals, television signals, radar and laser light, say 50 years. Being generous, our signals have traveled out in a sphere with a radius of 100 light years. That's about 1,000th the width of the Milky Way, which is 105,700 light years across. The nearest galaxy is Andromeda at 220,000 light years away. How long will we continue to broadcast? In other words, how long will our technological society last? Some think not so very long. We have to be realists. There will not be too many terrestrial-like planets with liquid water and an atmosphere to support life, nurture that life to evolve over billions of years into a sentient species that may just develop technology and an understanding of the cosmos to want to listen out and respond to a signal from space. There is most likely life out there, but it's not talking to us yet. Let's crunch some numbers. We'll take the arbitrary figure of 100 light years, where a sufficiently advanced society could detect our radio signals. They then work out where the signal came from and dispatch a response. This could take a few years to achieve. Then that signal will take up to 100 years to get back to us. 100 light years in kilometers roughly equals 9 plus 14 zeros after it. What stars are within that reach? We're only looking at main sequence stars, ones that are stable and long-lived, moving through various stages in their lifetime of billions of years. So we have 3,868 stars to choose from, plus a few more very dim ones we haven't found yet. Exoplanet hunters have been targeting the dimmer, smaller stars called red dwarfs or M-type stars because it is much easier to detect planets around them. There are 2,026 stars of that class in our region. They have also been looking at the slightly larger orange K-type main sequence stars. Because of their spectral and luminosity qualities, astronomers favor them for having habitable Goldilocks regions. There are 947 and counting, though there are only 155 within 50 light years. Then there's the G-type stars. Our Sun is a G-type, so they are highly regarded for habitable zones. There are 512 of them. F-types are slightly larger than our Sun, 303 are nearby, and several have known planets. A type which are young stars, a mere 100 million years old, and again have been found to harbour Jupiter-like gas planets, 76. B-type are giant blue stars and rare, only 4 in our region. And supergiant O-types are hot and hostile and nowhere near us. So, how many exoplanets? 3,700 confirmed exoplanets so far. Five Mercury-sized rocky worlds, 72 Mars-sized, 701 Earth-sized terrestrials. (982 called super-Earths), 799 Neptune-type gaseous worlds, and 1,217 Jupiter-sized gas planets. So that gives a current total of 1,683 Earth-like rocky planets. How many of these rocky worlds could harbour liquid water on their surface? Well, there is the habitable or Goldilocks zone around these stars, where the planets receive the right amount of solar flux, where water is liquid. Too close and the water would boil away. Too far and it will freeze, making life more difficult to evolve. So, scientists have estimated there are 17 definitely within this zone. But 3 are outside our distance limit of 100 light years, so that leaves 14. Plus another 13 terrestrials that could seed life, but be very harsh and unforgiving to it. That makes 27 candidates capable of harbouring life as we know it.
Life could be incredibly common, because there are lots of planets out there, or it could be an incredibly rare event that only happens, on 1 in a billion planets in a galaxy. We really just don't know. So whenever I get asked that question, my answer is, I don't have an opinion yet. I'll need some more evidence.
TREVIST-1, an M-type dwarf star at 39.6 light-years distance, contains a solar system of 7 terrestrial planets and is a major contender for harbouring liquid water, They're all Earth-sized candidates. Other multi-planet systems in our region include HR 8832, 55 Cancri, and 61 Virginis. The names just roll off the tongue, each with at least 3 planets orbiting it.
Well, looking at exoplanets, these planets around other stars, is a bit like detective work. They're so small next to a bright star that it's hard to tease out information unless you do it incrementally. So what we can tell right now is that these planets are in fact similar to Earth in size, and we can tell that some of them may be similar to Earth in its composition. Doing kind of crude studies of the density of these planets. We're also using the Hubble Space Telescope right now to do follow-up observations of the atmospheres of some of these planets to see the composition of the atmosphere, and wondering and trying to find out if maybe there might be water in the atmospheres to see if they are similar to our own Earth's atmospheres.
With names like TRAPPIST, Tau Cetus, Gliese 876, HD 219134, and Wolf 1060, these exoworlds sound ponderous and uninteresting. But one day they may be given more appealing names, because these are worlds with great potential. Elements such as hydrogen, helium, carbon, and oxygen abound throughout the universe, so we might assume that they are available to such planets, and therefore water would be plentiful. Even worlds completely covered in water are feasible. These basic elements also make up the active ingredients for life. And amino acids are commonplace, so microbial life could emerge on all these target planets quite readily.
Now, we strongly suspect, based on an example of one, our Earth, that the laws of biology work the same everywhere too. And by that I mean the laws that Charles Darwin discovered for us. We think that based on these laws, that evolution can drive life to greater complexity and ultimately to intelligence. It's the smart thing to do.
As with Earth, it could take billions of years for evolution to create ever greater complexity and eventually intelligence. On Earth, most highly intelligent creatures are of the mammalian family, but the octopus developed its intelligence through an entirely separate route. This would indicate that intelligence has many chances of evolving on these worlds. So, why are there no similar technological societies among these 27 candidate planets? What could be stopping intelligent creatures from developing technology, radios, and spaceships? There are several possible answers. Earth has had major climatic disasters that nearly wiped out life completely. Perhaps a similar disaster was successful on one of these other worlds and killed it. But even with these events befalling some of our candidate planets, there should still be 25 or more potential civilizations.
So, you'd think there'd be plenty of opportunities for life to evolve somewhere else and maybe swing by the Earth, or at least call on the radio. But we haven't found any alien monoliths, or beer cans, or cigarette ends, and we have not heard them tweeting on the radio either. So, where are they? There are lots of theories about that, but I'm going to concentrate on the more plausible ones. First of all, there's the water trap. Maybe the worlds that have water on them are all ocean, for the most part. And if that's the case, you can't discover combustion, you can't make metals, so you can't make a radio or a spaceship. If our dolphin friends lived on an ocean planet, they would be stuck where they are, in the Stone Age, forever. Or maybe on a planet that has dry land but no metals, or very few metals. Same problem, you can't develop a technology. And how about the difficulty of interstellar travel? Maybe it's just too hard. It looks like a real challenge for us. It could be a couple of 100 years before we try that. Maybe it's just too hard. And then there's another theory, which is that we could be the first. We could be the first intelligence to evolve in this part of the galaxy. Someone has to be. We could be the elder race. So here's a time history of Earth. When you look at all the time that life has been here, nearly 4 billion years, humans have only been around for a couple of 100,000 years, civilization for about 6,000 years, depending how you count it, and our technical era only for 200 years. When you look at this picture, it is obvious that the most likely first alien life forms that we discover will not be intelligent. They will be somewhere back here, equivalent to life on Earth during the first 3 billion years of evolution. Similarly, nearby life on an exoplanet is probably plodding its way up the evolutionary ladder. Remember how long it took us to get where we are, where we could even think about life elsewhere.
We Earthlings have the prime real estate in our solar system. We may well be alone for the moment in our section of the galaxy, the only ones with space travel. If so, we need to take care of our planet and our civilization, and stick around long enough to see other intelligences and civilizations emerge over the coming millions of years on those 25 nearby planets.